So my name is Anthony Brady. I'll be the instructor, one of the instructors here. I'm from work jointly between NIST, uh, National Institute of Standards and Technology, and University of Maryland. And my co-instructor right over there is Jack, and he's at the University of Maryland also. And today we'll be talking about information in a photon. So let's go ahead and get started. Um, Great. So just some suggested prerequisites, if you didn't see this already, is it'd be nice to have some knowledge of complex numbers and probability theory. These will be very useful in what we're doing because we're going to be going over essentially like the classical communication of quantum optical states. You can think of it that way. Some linear algebra, so dealing with matrices and vectors, particularly complex matrices and vectors, which show up in quantum mechanics, and some basic knowledge of quantum mechanics, at least in terms of the basic mathematics like measurements and states in terms of bracket notation and how to do and perform measurements. So the goals here, again, this is sort of the classical communication of quantum optical states. We'll be encoding classical information, so bits, into some quantum optical states like coherent states, and describing how we detect those, like noisy channels that we might send these quantum optical states over, and describe information rates and communication rates of these channels at a very formal level. I'll be doing a good bit of the mathematics and the formalities, and Jack will be talking about how we might physically realize these and some interesting stuff there, some interesting physics. Okay, cool. So we want to send a message. This is the whole point. So how do we do this? So so we want to send some classical message. So here we have some astronaut on the moon, and he has some message, one small step for a man. He encodes it. Of course, we can't he wants to send this message to Earth, but we're not going to send the astronaut all the way back to Earth to say just this one statement. So he's going to encode this into some digital information that's easily and reliably sendable. So we have a bit string here for the letter A. So what did you call this, Jack? ASCII? The ASCII encoding for
Yep.
the letter A?
Yeah,
Yeah.
it's the ASCII binary encoding for the letter A.
Yeah, so cool. So this is this ASCII coding for the letter A here is this bit string. So we'll encode it in binary, this into digital information. And then of course, we have to actually physically send this digital information somewhere. So this will represent this modulation scheme. In our case, it'll be light, in the state of light. And here it'll be represented by quantum state, right? So this is the quantum state of light that encodes this digital information. We'll send this over this noisy channel from the moon to the Earth. So it's noisy because many things can happen. We can lose the signal entirely, or some stray light can come into there or whatever. So on Earth, we'll get some noisy quantum state, psi prime. We'll do some measurement detection stage to try to decode what this guy sent. So we'll measure the light. We'll extract some digital information from this message, and maybe there will be some errors. So here, for example, you'll see these red places where a bit flip occurred. So a flip from 1 to 0 occurred in these two red entries. But we'll try to do some clever decoding scheme and actually, even when there's a small amount of error, maybe infer what the man said. But here, so Jack telling me that this actually, whenever these bit flips occurs, this is the ASCII key for this space symbol. So instead of one small step for a man, they receive one small step for man, and it's not too big an error for what they were doing. But in some instances, this errors might be bad, and we send the wrong message. Okay, so again, we want to transmit classical information using quantum state as a carrier. This whole scheme. This is sort of a high level description, so we'll be going over in detail how we do this, right? And we can use decades of classical information theory in order to analyze this kind of system. In quantum mechanics, we know that when we measure a quantum state, we perturb the wave function, particularly we collapse it to the whatever measurement setting we have. And so the choice of measurement is a very great importance. That's what quantum mechanics tells us. So we'll see that the measurement choice is actually there's optimal and very suboptimal choices of measurements for communication tasks. And we'll explore all of this again using quantum light to carry this classical digital information. So just for some background, so where's my? Oh yeah, I can do this here. Yeah. So complete knowledge of a system is in its quantum state. So this is a complex vector. So vector, we'll call it a ket because this is like we have a bracket and this is the ket part in a complex vector space. So psi is a unit norm and its conjugate is a row vector. So this is the bra part of the bracket, and it's the complex conjugate of psi, right? And so this is standard basic quantum mechanics. And yeah, so we have this unit norm condition. So a very simple example is a single qubit state or a two-level system where psi can be written as a superposition of a zero and a one. Okay, and these zero and ones form an orthonormal basis in distance. So their overlap is zero. So this is just some complex dot product between those two vectors is zero, while they're unit normalized. So that's these guys here. So again, you can just think of these as two-dimensional vectors, and their dot product is zero, and they're normalized. So in this notation, we can write psi simply as this right here. So these alpha and betas, these are complex amplitudes or probability amplitudes. That's important. That's what distinguishes quantum mechanics from standard probability theory, is that we can interfere these amplitudes and get some interesting quantum phenomena that pops out, while their modulus squareds are probabilities. So alpha squared is the probability to be in zero, and beta squared is the probability to be in one. Okay, I've done this, but how do I get out? Oh, there we go. Perfect. Oops. Okay, great. Right, so that was a little basics of quantum mechanics, crash course. Now I'll do a very super duper crash course in a bit of probabilities and random variables. We don't need too much here. There's just a few basic things that we need to know. And there's a lot of symbols and things going on, but there's two ideas that are prominent here. So we're going to talk about probabilities and random variables. So random variable is just right. I give you a variable k. So for the discrete case, I give you a discrete variable k. So it can only take on so many discrete possibilities. Right, either one, two, three, four, things like this. But I give you k, but we don't know exactly what it is in any given instance, but it has some average that it can take. Okay, and its distribution is its random distribution is given by this probability mass function, where the probability here sums to one. And the main things that we'll be looking at is for the discrete distributions is a Poisson distribution, which takes this kind of form where lambda here is actually just the mean of the Poisson process. It's also the variance, so this is actually a special probability distribution. So lambda here describes the mean and the variance. So this is actually the probability distribution for coherent states in a photon number basis. So very important. You can also talk about continuous random variables. So I give you a random variable x, let's say from minus infinity to infinity, and it can take on any of the values on the real line, right? So again, 1, 1.2, minus 1.2, and everything in between. Now, this random variable is not described by some probability mass function, but a probability distribution or probability density. So if it has units, this p of x has units of 1 over x. So it's really a density in this real space. this really, very common, prominent example is the Gaussian distribution, which hopefully everyone has seen, right? So here it has a mean mu, X has a mean mu, and then variance sigma. So in this case, oops, where's my little pin? So the Gaussian is just on the real line. It's written in this way, right? So this is the mean mu, and the width of this guy is sigma. And this is the real line. You can think this is the real line, right? Okay, good. And one more thing is that interesting phenomena occurs for very large lambda is that a Poisson process is approximately a Gaussian process for very large lambda. Okay. And so the Gaussian here is Gaussian of mean lambda and of standard variance lambda. So the mean and the variance are the same, just how I described it in these two cases up top. Okay, cool. Moving on. So that was a little bit of probability theory. That was a little bit of probabilities, a little bit of introduction to quantum states. And so what interpolates between these two is quantum measurements. So we can go from quantum states to quantum probabilities by quantum measurements. So generally, we describe quantum measurement or a von Neumann measurement. This is a projective measurement, a particular case of measurements, as a projection onto an orthonormal basis. Okay, so this orthonormal basis is just a set of unit vectors which are orthonormal. So you've seen these before. If you haven't seen this in the quantum context, but this is straightforward and in vector space, you can think of these as like coordinate vectors, x, y, z, and they're orthonormal coordinate vectors, right? And so this is a projective measurement. You can generalize this, but we won't need that for this course. Okay, so if a state psi is measured in this orthonormal basis, the kth outcome appears with probability p of k. So this is precisely this Born rule here is that if I project onto this orthonormal basis, then the modulus squared gives me the probability to land on that state, right? So quantum mechanics is a probabilistic, a little bit more than a probabilistic theory, but it's a probabilistic theory. Okay, so the state psi, in general, if we have this orthonormal basis, we can expand a state in any basis that we want, right? We can expand in this measurement basis in particular, and the expansion in this basis takes this form. So note from above, this is a probability, and I said before, this is like an alpha and beta, so this is a probability amplitude whose modulus squared gives you the probability. And see, this is where things get a little bit more complex. This is a real number. This is just a square root of probability. And this is a complex phase. And that's where we get quantum coherence and things like that from. So this is the specialty of quantum mechanics. Right. Okay. Fantastic. First poll question. We can get this started. So I'll go ahead and ask this, and then Brianna can, or is it one of us, Brianna or somebody can pull this up after we ask. So poll question 0. This is just to get you warmed up for a later poll question. So given a quantum state, general quantum state written in this form, what is the probability P plus to measure the state psi plus? So recall that the probability is just an overlap between this vector and our state. All right, and also just a little hint, recall that also this holds. These are orthonormal in this way. 0. So this should be quickly calculable. So what is this probability? That's the poll question. And we'll give you about 60 seconds to answer. So tally up your answers as best you can. Oh, okay, great. Yeah, so about 69% of people said D, and that's the correct answer. So Great. So yeah, this is the answer for if you were projecting onto the zero state. This is the B is the answer if you were projecting onto the one state. Alpha squared plus B squared equals one. So this is just the sum of all the probabilities. So that's not the answer. And this is the answer if you're measuring onto the plus state. I mentioned before that these alpha and betas are complex amplitudes, so this is actually interference effect going on here, a sum of alpha plus beta. These are vectors, so these can interfere in some way for to get quantum phenomena. Okay, fantastic.
Okay.
And so now we'll move out of this basic quantum stuff and get on to some cool, little bit of cool physics and communication.
All right. If you could stop sharing, then I'll be able to switch. It won't let me take over. There we go. Desktop mode. Okay. Okay. So, as Anthony said, we've kind of done a little bit of introduction now of just some of the essentials that are necessary for this course. And now we're going to be moving more into the regime of looking at some of the physical background of modulating light, controlling the information in the light, and talking about optical communications more generally. So, the first thing to note is that information is physical. So, information can be something that is produced without even thinking about it, right? Like, so when we talk, we're speaking through sound waves that carries information in the sound waves. We use radio all the time. It's all around us for our phones and telecommunications. And light is something, I mean, we see with our eyes. There's information embedded in the physical world around us. And even our DNA is really an information carrier and propagator. Generally, we talk about two things: information transmission or communication, and then information processing or computing. So this course is going to focus exclusively on the communication side of things. And when we're trying to communicate, we want to choose the information to be embedded into a physical system or a medium that is controllable, fast-moving, predictable, and energy efficient. And controllable and predictable mean both the ability to put information into the light and to extract the information out. So that way we can do some sort of processing with it. Traditionally, the way that we've done this is with radio communications, at least on a large scale and for large distances. So radio waves are an electromagnetic wave. They have long wavelength, typically longer than 1 millimeter, typically much longer than 1 millimeter. They can pass through many materials around us, and they're ubiquitous across Earth and space around us. They're able to be used for simple communications purposes like radio, fireside chats, or they can be used for really state-of-the-art communications, things like sending signals back from Mars off the rovers, or in our modern phones, which also use radio and microwave communications. What's nice is that this is a well-developed technology. We've had decades of experience in building transceivers and choosing modulation formats, and we'll learn about how some of those things connect to optical systems. But note that it also travels at the speed of light and has fairly minimal background noise when you're not into too noisy of an environment. But over the last 2 decades, maybe three, you could say that there's been a major transition towards optical communications wherever possible. So right now, most of the information that's flowing over this Zoom session is passing through fiber optic cables somewhere underground. And these fiber optic cables, like the ones shown here, they carry light in them, usually invisible light, so it's infrared, around this 1.5 micron wavelength. And it's passing through millions and millions of fibers all around us, and it's carrying a huge amount of data. So because this wavelength is much shorter, this 1.5 microns, it allows us to put more information into a denser time period, so it has a higher bandwidth. In addition, the size, weight, and power of the transceiver systems are typically much, much smaller than radio communications. So here is an example of a laser diode next to a penny. This is just one example. There are many sizes and shapes, and they can even be integrated into semiconductor wafers themselves. Um, so very small. The fibers themselves are obviously very, very small. For the purposes of free space communications, this satellite in the bottom right corner here, this is the Psyche mission or rendering of it. So it's a satellite called Psyche, and it's also on its way to the metal planetary proto-planetary body called Psyche. So it's out past Mars is where it's going right now. This was launched in October of 2023, and it has both a classical radio frequency communication system. So this large antenna that you see here, this is a high gain antenna pointed back at Earth. And it's probably almost impossible to make out on your screen, but there's a smaller black dot you can kind of see here near where my little pointer is. That is the deep space optical communications platform on board this mission. So it's a demonstration of optical communications at extreme distances. We call this deep space optical communications, and the mission is named appropriately so. And it's already the furthest demonstration of this technology, and it's providing huge amounts of data that actually is becoming close to the primary link for this mission. And so you can see the reduction in size required to go from a large antenna like this down to a smaller aperture to get an even higher data rate, actually. So now that we kind of have the context of what we're talking about with optical communications, we need to hammer out really quickly the definition of the light that we're going to be working with. So, like radio waves, optical light waves are also electromagnetic fields. So they're co-propagating electric and magnetic fields. In our little diagram here, the blue is the electric field, red is the magnetic. Um, they are in orthogonal planes, and we're almost exclusively going to care about the properties of the electric field. This is what physically interacts with most devices, including the photodetectors that we're going to be talking about. And we won't dive into the specifics of it, but the semi-classical theory of photodetection falls from the electric field interacting with the atomic systems in the detectors. So when we talk about this field, we need to consider that we have this monochromatic plane wave. So this plane wave is propagating in one direction. So it's in this case propagating directly in the z direction. Um, and it has a definite polarization, spatial, and temporal mode. So here, what I mean by a mode is that this field occupies some state of both space and time, as well as a polarization that is unique to it, and it satisfies the Maxwell equations. If we were to write this out explicitly, we can look at this positive wavelength or positive frequency component of the field. So this electric field has both this notation for generally one of two polarizations. So you could think of this as being the E field either pointed in the X or the E field pointed in the Y, often denoted as vertical and horizontal polarization. And we need to consider both those components. And we're going to integrate it over every possible wavelength generally. So this omega is the angular frequency that is equivalent to the wavelength. We have this scalar amplitude, and then we have our complex amplitude, which is a function of the wavelength. And then we have our oscillating component, so this e to the minus I omega t. And finally, we have this mode component, so this u function. It has spatial, so spatial in R, as well as frequency components or temporal components, so the omega and the t, and it has a definite polarization. For our purposes, we are going to look at a specific mode structure that looks like this below here. So we call this a flat top monochromatic pulse. So we have a single wavelength or a single frequency omega, and it satisfies the Maxwell's equations. And we're going to pick a definite polarization. So we can just for our purposes imagine that it's a vertical polarization like this, and it occupies a discrete amount of time. So this specific flat top pulse, we can then simplify the characterization overall. We can say that, okay, I don't need to write out the entire field structure here every time. I'm going to assume always that I'm working with this U that represents a specific mode. And in addition, I can call this state a quantum state. The coherent state of light is what is naturally emitted from an ideal laser. And this alpha characterizes the complex combination of the scalar amplitude and the angular component. And so I'll write this alpha inside of a ket, and I'll assume that I have implicitly defined a polarization, spatial, and temporal mode. So this alpha really is going to characterize the state of our light. It carries the amplitude in the phase. And for our purposes, we'll get rid of most of these subscripts for simplicity for the rest of this talk. And we'll just assume that whenever we have a ket with an alpha inside of it or some other coherent state, we already assume there's a mode assigned to it. And an important characterization of this field is also that it carries an amount of energy. And you can calculate the average amount of energy present in this field by taking the mod squared of this complex amplitude. So mod squared of alpha, and that gives you n. And this n is the mean photon number of the state. So a lot of definitions here, but safe to say when we talk about alpha for the rest of this, and you see a ket like this, picture some sort of plane wave like this with a flat top. And to go a little further and make it even clearer, um, we can often represent the phase space, we can use the phase space representation to show what we're talking about in terms of sets of modulation of different coherent states or comparing how coherent states transform in certain channels. So the phasor diagram allows us to visualize the complex amplitude of the state. States of equal radius carry the same energy, quantified as the mean photon number n. So let's start with alpha 1 here. So we assume that all three of these are effectively different ways that the same state or the same mode could have energy in it. So imagine the same set of time, 0 to tau, same polarization, same wavelength, but we're saying that I can excite that field in a different set of possible ways. One way I could excite it is with this alpha 1 here. So if I were to visualize this, it would be here on the phase space diagram, and anything on this unit circle would have a mean photon number of 1. And so these would just be different phases of the same state of light. Different coherent states, though. Same thing with alpha 2, so stronger amplitude, different phase. And finally, we have this alpha 3, which is way out here. So these would each have their own respective mean photon number, which would be the same as any other one on that unit circle. The zero amplitude state is called the vacuum state. So this is no excitation in the field, just the vacuum energy present. Okay, and on to another poll question. So a quick check. What degrees of freedom define an optical mode? And they're written out here, options A through D. So I don't think I'll read through them all if we can kick off the poll. Okay, awesome. So we have 2/3 correctly said spatial temporal polarization. That's great. I will note, so some people might say, well, what about the wavelength? The wavelength is built into that temporal structure. So really, you could actually call the temporal one the temporal spectral. It's a combination of time and frequency. In our case, we've strictly said we're working with a monochromatic wave. So it's all built into that temporal structure. So good job.
By the way,
Okay.
I think there's the chat's not open, but I think there's a Q&A. If people have questions, then I can either me or Jack will. Yeah, there we go. Thanks, Brianna. Yeah, there's a Q&A. So if you have questions while Jack or me are giving our lecture slides, then I'll try to answer them in chat for you if Jack doesn't answer them just as he goes along. So
Cool. Good thing to point out. Okay. Question 2. Which of the following is not a benefit of optical communications over RF or microwave communications? And again, we'll just throw it up and see when we get a good amount of responses. But yeah, which of these is not a benefit of optical over RF? Okay, we've kind of got a mixed result here, and I'm realizing part of that is that I did not address D earlier. So I think I had it written in the slide, but I didn't say it out loud. So the correct answer is A, lower time of flight. So both fields, RF or optical, will both travel at the speed of light. Um, that's going to be the same either way, so we can't beat that. D is something that I didn't address, which is that for RF communications, like our cell phones, there is a set spectrum that's available, and wireless carriers or space satellite operators need to purchase parts of that spectrum at huge cost in the billions of dollars to be able to operate in that regime. That is not true for the optical spectrum. So there's no spectrum cost that you have to purchase to be able to use optical communications. So the correct answer is A. But yeah, for those of you that selected D, you're right. I didn't address that. Okay. Now, we've talked about optical communications here and some of the essentials of the light that we're going to use. We're going to, for the rest of this topic of information in a photon, we're going to dive into a specific regime of operation for optical communications that we've already alluded to, and that's vacuum-free space. So this is when we're sending some signal from somewhere in physical space. And for the simplicity of it, we can say it's going back to Earth or to a satellite near Earth, and we'll ignore the atmospheric effects for now. There are free space communication channels. In fact, there's a whole field of research around atmospheric free space, which has a ton of nuance that we're not going to address in this case. Ours has its own separate set of problems that we need to address. And while we're not going to talk about some of the details of fiber optic communications, we will be borrowing some ideas from fiber optic communications because it's a very well-established field. And I'll point out that some of the technology does carry over from what's already been developed there. So to define our vacuum free space channel, there's a few key components. The first is a transmitter. So this image in the upper left here, this is a micro CubeSat transmitter, actually, transceiver. So the light is coming in and out of this tiny little aperture here, which I believe is just a few millimeters in size. It's one of the smallest ones deployed onto any satellites. So this one wouldn't even go to deep space. This would be something you would put in low Earth orbit. It has a laser inside here and its own modulator, and it's going to send the light to come out of the transmitter. It will propagate some distance r, and it will diffract. So throughout this time, it will spread. This is an inevitable feature of using optical communications and any magnetic radiation. If you are not confined to a waveguide, you are going to see some spreading. Um, the light that you pick up at your receiver is limited to the size of your aperture. So if I have something like the Hale telescope here, I have a huge aperture, and so I can collect a lot more light than if I have something really small. An example of this for like a real system, so you would never actually pair these two things together. This is just two extremes, the smallest transceiver in space and the largest receiver on Earth. A more typical pairing might look something like this for deep space. So this is the a rendering from the Lunar Laser Comm demonstration. So this was a 2011, I believe, demonstration of using optical communications from the moon down to Earth. So this is the transmitter and receiver, and of course you can go the other way, but oftentimes what we care about most is this downlink, because this is where we're limited in power. We're limited in power because our spacecraft only has so much available power at any moment from the solar panels. And we can generally build bigger optics on the ground if we need to. So this is the downlink is usually the most mission critical of these. Also, we're usually for space missions, we're trying to send data back from space to Earth more than we are from Earth to space. Not always the case, but generally. And so we have these key components, these transmitter with an associated power level. So there's a transmit power, and you can also make that proportional, or it is proportional to the mean photon number when we're talking about the coherent states of light that we're using to transmit. We talked about how diffraction induces a spread, and the receiver detects the portion of the light that's incident on its aperture. So we have this ARX. Uh, and finally, then we can calculate the overall received power, which is just a function of the incident power, the transmitter size, the receiver size, and inverse square proportionality with both the wavelength and the distance traveled. So shorter wavelength, less diffraction, shorter distance, less diffraction, as you would expect. But often we're locked into a wavelength, so we can't really tune that too much. We're usually using that 1.5 microns. Sometimes people use like 810 or 1064, but the biggest limitation is that there's two. One, most of the equipment that we have developed is for 1550, thanks to the fiber optic communication industry. And two, there's a really good visibility window through the atmosphere at 1550. So all things together, it makes it kind of ideal to use that. In the distance, that's just something that's dependent on what your mission profile looks like. So yeah, if you can't increase anything else, you're stuck at this power level. For deep
Hey,
space missions, typically this power level drops well below 1 photon per symbol.
hey, can I just interrupt you real quick, Jack?
Yeah,
Someone asked in the Q&A about the poll question, what was the meaning of option C? It's the swap, size, weight, and power.
yeah, I
Uh,
talked about that. So the size, weight, and power is the overall mission structure, or the overall. I mean, you can look at this satellite right here too. So
yeah, that's why I wanted to bring it up now because this is actually where it is important. This swap.
yeah. So I'll address it again here. So the size, weight, and power comes from the fact that the physical wavelength that you're transmitting is much shorter for optics. So you can imagine your aperture actually is smaller. So if I go back, what I showed before. So on the Psyche mission here, remember this is a large transceiver for RF communications, and the smaller one is for optics. And the power associated with driving the electrons in this larger transceiver Um, it costs a lot more power to push a bunch of electrons around over this huge thing than it does to have the light be modulated from your really energy efficient laser. So the size, weight, and power. The weight kind of comes with the size inherently, but yeah, you get an improvement there, a pretty dramatic improvement actually. Um, so yeah, in this system, you can kind of see some of the RF communications here. It might be small on your screens, but yeah, you can see components of the LLCD mission that are the radio comm systems. And again, the laser comm system is much smaller. There are other challenges that come with it, like pointing accuracy, but many of those have been addressed in deployed systems over the last 2 decades. Okay, so to hammer a little bit more the connection between the coherent states we're talking about, the noisy channel, and our received state, we're looking at the same type of system here. So we again have a transmitter up at the top and a receiver at the bottom. In this case, I've shown a gradient here to introduce the density of the state, right? So like how much energy is present per some unit area or the intensity. It starts out really strong, and then as it spreads out, the intensity is going to weaken. And so we have a transmitted coherent state, which is what we start with here. And it really, this whole time, is still the transmitted coherent state. It's just spread over a much larger distance. And then the received state is what we get coming from the other side of the aperture at the receiver. Um, this is also a coherent state if it's properly captured. And the coherent state that we can write here, this alpha received, we'll parameterize this with this eta, this transmissivity. So root eta alpha transmit. This eta is ranges from 0 to 1. For deep space, it's going to be very, very close to 0. So we're only going to capture a very small percentage of the energy that's actually coming to us. This is not really to scale. We're going to capture extremely small amount of the light because we're always going to be, limited to a few centimeters or maybe up to a meter or two for our receiver aperture. Our mean photon number also scales. So our transmit will always be higher than our received, and it's going to scale with this transmissivity eta. And if we want to go to our phasor diagram, simple picture, if we imagine that we've kept the phase, so these are both in line at the same phase angle, but our mean photon number has dropped, and so we've gone from alpha transmit down to alpha received. This is the pure loss channel, which is the one we will focus on when we're talking about vacuum optical communications. There are all sorts of other channels that can induce different types of noise. But for the purposes of this class, we're going to try and work with this pure loss channel and figure out how we can handle optimal communications at the extreme end of this pure loss. Now, to kind of start to address how do we put the information into the light itself, this topic is called modulation. It's something that's done with radio frequency communications today and fiber optics. And there's really two general categories of modulation. One is analog modulation, and the other is digital modulation. Analog, I'm taking some continuous signal. In this case, it's something like this RF sine signal, and I want to transmit that on some carrier, the optical field here. So I'm going to put my RF signal into a modulator along with my carrier, and out comes my modulated signal. There's different ways we can modulate. For radio, all of us, I think, are familiar with AM and FM. So in AM, we're taking this RF signal and we're attenuating the amplitude of the carrier to match our RF signal. So um, this amplitude is a function of our RF signal. Actually, it directly mirrors it. And alternatively, you can use frequency modulation. So this would just be changing the frequency of the carrier. You can do this in optics too, although it's less common, but it is possible. We would typically do the phase modulation here instead of frequency. And so you can see that down in this digital modulation below. So here's another optical field. Now, instead of sending the uh, continuous analog signal, we're going to send a digital signal. So during one period, we want to send a 1, 0, 1, 1, 0. We're going to put that in. And then during each of our time periods, so this would be like the 0 to tau we saw earlier during our flat top definition of the mode, we're going to attenuate our signal. We're going to modulate our signal. So this would actually be another frequency shift keying. So we're shifting the light. The one we're going to talk a lot about here is this phase shift keying. So we're changing the phase, in this case, by a pi phase shift back and forth. You can also do intensity modulation in light. That's perhaps the most intuitive thing to think about is just turning the light on and off to represent the digital bits. Um, However, there's a nuance to that, which is when you aren't receiving any light, it's hard to be sure that you're actually pointing at the right place and that your clock is correctly set. So there's typically, if you're going to use intensity modulation, there's an additional nuance, which is that for on-off keying, as this is called, there's a return to zero. So um, even if you're sending a one, you go back to zero for a moment, and that helps you keep the clock cycle. There are other similar ways you can structure this, but the fundamental thing is, yes, you can take light and you can modulate it on and off, and that will give you an ability to embed information into the light, just like you can do with amplitude modulation in RF. So for optics, the things we can modulate are generally the phase, amplitude slash intensity, and the frequency. And we're going to focus on these first two almost explicitly in our case. Uh, the way that this is physically done, it's easiest to understand it in fiber, where we have light that is confined to an optical fiber. So it's coming in from the left here. It enters into this waveguide. So this is some sort of nanophotonic structure that's been crafted that couples light from the fiber into it. We won't go into the details of how this functions, but this would be like a Mach-Zehnder interferometer, where by splitting the light into two arms, and applying a voltage to one of the arms, we can change the local refractive index in one of the arms. And then when the light recombines at this side, um, it has a self-interference, and we can generate either a change in the intensity or potentially the phase if we just have one arm of the light. So in this case, we're sending in the light. Let's imagine that it's all equal intensity the whole way in, and we want to send this digital signal. So this would be like a zero and this is a one. We apply that with an RF cable that modulates this one arm, or it changes the refractive index on this one arm, and that together with the interference at the end generates our modulated optical signal at the output. Um, these things are incredibly common for fiber communications. So this is a picture of what one looks like. This is a 10 gigabaud per second integrated optic intensity modulator. So this one, just like this, is modulating the intensity. There are equivalent systems that modulate the phase. There are also ones that can modulate both the phase and the intensity slash amplitude. And you can see this port right here, this little SMA port. This would be how you input the signal that is driving your modulation. Lithium niobate is really a common material. You might hear that if you're kind of looking around. It's a really common material for this this modulator to use to actually change that refractive index. And you can buy these commercially for all sorts of prices, and oftentimes they're integrated into even smaller pieces as opposed to like dedicated fiber coupled ones like this. But when it comes to the free space optical communications, you can use basically the same structure because most of the time our light is either starting in fiber or is coupled into fiber at some point during the transmit side. So very, very similar structures or components can be used. Um, yeah. Now, we're going to talk a little bit more about some of the specifics of the modulation that we are going to use, and specifically those that are useful for deep space comm. We already talked about on-off keying. So that's where you're just turning the light on and off. So on would be the one, and off would be the zero state or the vacuum state. So either have energy present or not. And we can calculate the mean photon number for each of those states. That's useful. But actually, a more useful system for communicating many bits in a single pulse is called pulse position modulation. So this on-off keying, this is a binary encoding. So you can only send one bit during each of your pulses. Now, if you allow yourself to have more intervals, so each of these spacings here would be something like, in this case, 1 nanosecond. We could call that our 0 to t would be the 1 nanosecond. If I allow myself to send a lot of vacuum states and then put a large pulse into one of those, it increases my chance of being able to actually detect that state of light. And then I can decode, depending on which interval it was in, which bit is sent to me. So if I'm trying to send, I think this is 16 time bins, so this would be 4 bits. So I'm trying to send you 4 bits of information. All I have to do is put the light into one of these slots, the emp slot, and then when you detect it at the other end, you can decode all 4 bits simultaneously. And we'll talk more about the detection stuff in a bit, but this pulse position modulation is relevant because this is the primary modulation format used for deep space communications today. mostly due to another factor that we'll see later called the photon information efficiency. Um, and the number of modes used in missions today can range from lunar missions can be around 16 to like 64 modes, and then you can go all the way up to several hundred when you're looking at like the DSOC mission on its way to Mars. Um, and in the lab, people have done much more than that, but for practical purposes, you need several hundred modes to go to truly deep space. An alternative type of modulation, we already looked at a little bit as well, is the phase shift keying modulation. So we showed this in that simpler diagram, but to dig into it a little bit more, the binary phase shift keying is where I always send you a state of light. So there's always light in the same amount of energy coming during every pulse. But I'm changing the phase and I'm encoding my information there. So the alpha would be this state, and that would be like we can call that our one, and then the minus alpha would be this other state, so it's just pi out of phase. That would be the zero. So I just alternate sending these to you. The nice thing about this is that you're always sending the same amount of energy, so you don't have this really high peak power requirement. You're using a steady amount of power, and you can use a CW laser, which is really energy efficient to just kind of always keep your light going. This also allows you to just send 1 bit during every pulse, just like on-off keying. You can also take this further and you can do things like Q-array phase shift keying. So instead of just allowing yourself to have the two pulses or the two possible symbols, alpha and minus alpha, if you break up your unit circle for your state into Q different possible modulations, you can pack in log Q bits. So in this uh, 8 PSK, you'd be sending 3 bits during every single pulse. So if you can properly decode this, you can send a lot more information during a single time pulse. If this is, say, this 1 nanosecond, um, you can take this even further. And instead of just modulating the phase, you can modulate both the phase and the amplitude. So this is quadrature amplitude modulation. This 16 QAM would be sending 4 bits during every single pulse period. So you would transmit one of these during every 1 nanosecond. And then if you can properly tell which one was sent to you, you can decode 4 bits of information from that. There's an added benefit that is a really interesting fact about this, which is that you may not want to send all of these with equal probability. So this higher energy one, like in the corner here, this is at a larger, you can imagine a larger circle of equal energy around it. So you might not want to send that one as often as one of these ones that has like a lower energy cost. And if you could imagine a 2D Gaussian, maybe hard to imagine, but you can change the rate at which you send each of these codes to optimize your communication capacity. The larger and the larger your QAM goes. This is not really useful for deep space communications. There's far too much loss to be able to decode between these. But it is practical in fiber optic communications. So you will often hear about QAM in like data centers or even some long haul communications. Okay, another poll question. So, which of the following modulation formats is the most challenging to generate? Analog, just an analog signal, 16 QAM, a BPSK modulation, or 32 ppm? Okay, so we got a little bit of a mixed result, but the majority did go with 16 QAM, which is, I would say, the correct answer. 32 ppm could be, under some situations, difficult to generate if you consider that you probably would want to use a different laser system. But 16 QAM would be the one that typically would be the more challenging one that you would actually have trouble sending. So yeah, that's what I would say the correct answer is. For those of you that answered BPSK, I think maybe you're thinking that because I guess I'm not sure what the logic is there. That one should be relative. That one's like probably the easiest to generate out of all of these other than analog. All you're doing is applying a like you basically have two voltages that you're hitting your modulator with, and you're just alternating whenever you need to change your bit. So there's only two possible values of voltage you're sending. So that one's really easy, and it's actually one that we're going to focus on for a lot of this because it's useful due to its equal energy properties during each time pulse. But yeah, the majority got that right, so good job. Now, there's another format of modulation. Actually, there's a whole realm of formats of modulation that I am not going to dive into here. That's really interesting in theoretical talks and in some lab experiments today, which is we'll call it this non-coherent modulation, this quantum modulation. And this would involve sending either uh, a discrete number of photons. So, like, let's say I encode my information by how many photons I'm sending if I have like a quantum dot or some other single photon generator. And then I decode how many photons were sent to me. That has a lot of practical implications if you could realize it. Unfortunately, it's very, very challenging to generate a deterministic number of single photons, especially at a high rate. And also detecting them is incredibly challenging with precision as well. So this is an interesting thing, has potentially useful applications in the future, but is not practical here. An interesting thing to kind of think about with these is that when I've shown you the phase space diagram for the coherent states, I've always shown them as a circle. A similar type of visualization is the Wigner function visualization for a coherent state. If I were to visualize it, it would just be basically a Gaussian blob. But for single photons, they have these like Hermite type structures where you get this dip into a negative amplitude and then raise up to a positive amplitude. There's a lot of cool stuff to consider here. We aren't going to dive into this, but if you are interested, you can look up quantum modulation or single photon modulation. Okay, so
Oh, Jack, one second, sorry. Before we move along, we've got like several questions in the Q&A about different about modulation. So
okay,
multiple
modulation
questions.
questions. Okay,
Yeah. Do you mean just read them off to you one by one, maybe?
yeah, because I can't see them right now. So
Yeah. So the first one is, could you go into more detail where 16 QAM will be harder than 32 ppm?
yeah, so the thing about the QAM is that if you imagine, so I showed this modulator earlier. In this case, we have this single signal that's coming in, and you can see here it even says in this port RF. Well, maybe you can't see it. I don't know. It's hard to, it's kind of small even on my screen. Um, you are sending in a signal here, and your RF signal is effectively changing during that same duration. It's either going to change the intensity or the phase of the light that's going through one of these arms. So this Mach-Zehnder modulator, Mach-Zehnder interferometer down here, what's inside of this box is basically the same as this. This is an intensity modulator only. So it has like one arm here with one signal coming in, and you're applying that. If you want to change the phase and the amplitude coherently, you need to be sending in two signals, your I and your Q signal. And one of the trade-offs is that immediately you're going to have more of these little steps of Mach-Zehnder interferometers. So you're going to probably have more loss, unless you want to pay more money. In addition, you need to be able to assure that you can draw, that you have enough strength in your light that you can effectively allow these different intensities to be sent and these phases, such that if there's loss in the channel or phase noise, you can properly decode which of them they are. Now, just in generating it, the complexity comes from the fact that you need to have two signals to generate it that need to be properly like aligned. And the voltage needs to be properly tuned as well. So there's another nuance to this, which is that each modulator will have its own characteristic voltage. So there's this like V pi that's required for every modulator to drive all the way from this 0 to 1. And this can be anywhere from 1 volts at the like extreme low end with some research grade devices to typically like 2 to 3 volts. So if you have multiple of these signals in here, so if I need to do both intensity and phase simultaneously, I need two different RF cables, each driving that. And it's just a little bit more power dissipation as well, especially if you want to go at really high data rates. So there's nuances. It's not to say you can't do QAM. It obviously can be done, but it certainly is harder than BPSK. Now, as for PPM, the reason I would say that it's harder to do QAM as opposed to PPM is you can imagine that. So to do QAM, I already have to have a modulator that can modulate both the phase and the intensity. Well, if you say, okay, I have a CW laser, so it's always pumping at this same power. I'm always sending the same amount of energy. If I already have a laser that during, or sorry, if I already have a modulator that I can turn the intensity on or off, well, now in this case for PPM, I can just keep it off basically the whole time. I'm applying a constant voltage all the way here, and then only for this moment do I turn it on. So it's actually like a lower bandwidth needed for your signal there. Now, the reason I said there's some nuance to this is that typically that isn't the way you would do it. Like that would be a very energy inefficient system, but it would be the easiest to implement, where you have a CW laser and you basically just hold it off the whole time, and then turn it on. Um, More often you use what are called Q-switch lasers, which we won't go into. So maybe you could argue it's more complicated because you need a different laser system. And I could buy that argument, but if you're just talking about not worrying about the energy efficiency, this has a much lower bandwidth required to actually drive it than Quam. So hopefully that clarifies things.
Yeah, I think so. We got two more. Maybe we can just answer these on surface level. The first one is, what about PWM? Does it end up being like PPM but worse?
So PWM.
Um, what is, yeah, what is
I feel
PWM?
like I've heard of that before, but pulse pulse wavelength modulation, maybe. I mean, if it's a frequency type modulation,
Oh, pulse width modulation,
a
maybe.
pulse width modulation, yeah, yeah, yeah. So it's very similar, very similar. You can do that as well. People like pulse position modulation because you can, um, because of the effectively the Q switch lasers. So that kind of relates back to what I was saying. Q switch laser will have a definite period over which that switch occurs. Um, but if you were going to use the simpler version, like I was talking about, where you have a constant CW laser, then pulse width modulation, yes, that would be just as easy to do and would have benefits similar to PPM. But in practical free space, like deep space stuff, you're usually using a Q switch laser. And so then you don't really have pulse width modulation.
Okay, and then final question. The modulation might be easier to generate. A modulation that might be easier to generate may or may not be easier to demodulate. So that's like a
Yeah, that's true. I mean, yeah, they don't necessarily go hand in hand. Like I would say that, yeah, it's maybe harder to generate BPSK than it is PPM. But PPM is easier to decode than BPSK. I guess it's highly dependent on your system, but yeah, they don't necessarily go hand in hand. And in fact, we'll see over the rest of this course that the ease of generating one of these modulations pales in comparison to designing a receiver that can properly maximize your photon information efficiency or extract the most bits per photon in the high loss regime. So that's kind of a good question. That's actually a prelude to kind of where we're going to lead to next.
fantastic. All right, thanks, Jack.
Yeah. So with that, so let's take hold of where we are. So in our simplistic diagram, we're saying, okay, we have some digital information. We want to put that into our quantum state, which is the carrier. In our case, we're going to consider these quasi classical states, the coherent states usually. They are going to transmit over a physical channel. And so we're going to get some transformed noisy state. We've also made the simplification, which is appropriate for deep space, that we're going to look at the pure loss channel. So effectively, we're taking a coherent state alpha to some root eta alpha, which is our state. Now, we've talked about how you modulate that, at least some of the options, some of the challenges there, but we know what options we have. We need to figure out how to do the detection here. And so what options are available to us? And then how can we take later into account that this is all part of a larger communication system, and we need to choose the modulation and detection together to maximize the rate of communication. So I think maybe some words that I just said. We've seen that we can encode information into light via modulation. We're transmitting light over vacuum free space. And now we need to understand the tools available for detection. Okay, cool. I said all the things. To do the detection analysis, we need to dig a little bit more into the structure of the coherent states. So I said these are quasi-classical states. This is what's emitted by an ideal laser. And we're back to our alpha here. You can write the coherent state in this mode as being a linear combination and superposition of these Fock states. So these N states, these are like the photon states that we were just talking about. So the vector N is all zeros except for there is a one in the position of the number of photons, right? So N equal, if this is two, that's the two photon state. If it's three, it's the three photon, kind of intuitive. You can write a coherent state as this linear superposition of the Fock states. And so these are the expansion coefficients. Now, when we write out the state like this, it becomes evident that if we take two different coherent states, we take our coherent state alpha and then some other complex amplitude beta, and we take the inner product. We can write it out and we get this analytic solution for it. But this can never go to zero. So no matter how strong your coherent states are, they will never be truly orthogonal, which means you can never perfectly tell which one was given to you. Even if you had the best possible receiver, you can never perfectly do it. That's the inherent noise of the measurement that comes from these states. What we can say is that, okay, if I have a system that can measure the Fock states, so I can measure the number of photons, the probability of observing k photons when measuring the state alpha with this orthonormal basis, so this is, for clarity, this is a von Neumann projective measurement into the Fock basis. I'm taking my coherent state and I'm saying I'm going to project it into the measurement vectors with n. So I have all these possible n's that I can project into. The probability of generating k clicks, so this would be how many photons I'm generating, is Poissonian distributed. Um, we're going to continue on this in a second. Just for clarity, if you want to, you can also, from this definition, you can work backwards and find that the mean photon number is in fact mod alpha squared. We won't go through that, but yes, if you want to, you can work back now. You have all the facts you need to get that. Yeah, coherent states follow Poisson statistics. Why this matters is in a physical realization of this is if we imagine our flat top square pulse that we've been working with, and we put it onto this ideal direct detection. So this is an ideal photodetector. It's going to, what happens physically is that the light itself is going to generate individual electrons at certain times. So there will be an electron generated, and we'll imagine that that's something that we could detect. So we have the charge Q, and then we have K of them. So K clicks from our square pulse here. And again, this is a Poissonian distributed number. So if we know the mean photon number of our light coming in, and we assume that we have this direct detection, which is not exactly true in the real world, but we can get things close to this. What is important is that we can have what are called like bucket detectors, where if we just want to know whether we got zero or one or more photons in the regime we're working in, that's all that really matters because we're always going to have very, very few photons. But this Poissonian statistic will allow us to figure out, given some n, and we want to know how many photons, what is the likelihood of detecting a certain number of photons, we can calculate that really easily. And so this measurement is available to us. We'll say that this photon number basis or Fock basis measurement is one that's available to us in our communication systems. Now, we don't just want to do that all the time. We want to look at what other tools we have. So we assume one of our tools is this Fock basis measurement. We also have linear optics. So we can take our light and prior to the detection, we can process it with other optical components without really collapsing the state. So the information is being preserved. Um, yeah, there's a lot on this screen, I realize. So as with any state, light can be transformed through unitary transformations without losing any of the information. Several operations are easy to implement with standard optical components. These components are usually beam splitters, phase shifters, and optical delay lines. Um, yeah, the benefit can come from transforming the light into a state that is more well suited to the detector or our measurement that we're performing at the detector. Um, the way that a beam splitter works, that's probably best to understand here, is that imagine that I have two states coming in different path modes. So they're physically separated out is the easiest way to imagine this, just in a square like this. They come in, alpha 1 and alpha 2. They interfere here at the beam splitter, and I generate two new states coming out, beta 1 and beta 2. We can write this unitary transformation. So in the Heisenberg picture, I have these two states that come from alpha 1 and alpha 2 with associated field operators. And I transform them via unitary action to beta 1 and beta 2. And this is the general two-mode unitary operation. So if you look up the beam splitter operation or like the SU2 operation, you might see different forms of this, but they're all equivalent up to a phase. And the thing that we're going to consider here is that it allows you to do a few different things. You can create destructive slash constructive interference. So if I have these two states that are pi phase shifted and I put them into a beam splitter, we're going to get constructive interference on one arm and destructive on the other. So all of the energy is going to go into one of the arms. One thing I should note, so generally we characterize two parameters for the beam splitters. Eta is the transmissivity and phi is the phase. So you can see that up here, this theta is transforming the transmissivity, whereas phi is just the phase. So this would be a balanced beam splitter. So it's a 50-50 beam splitter, no additional phase being picked up. We can also do a pure phase shift. So if we are trying to look at this one here, it would just be basically a mirror. So we have no transmission and then we have some phase. So one side would pick up no phase at all, and the other, when it bounces off, picks up some phase. So what this is saying is you're creating a relative phase between these two that did not exist before. So if you imagine that you have some alpha and beta both on your unit circle or in your phasor diagram, you're rotating the beta one, but you're not rotating the alpha. Finally, one that will be important for us is this nulling and displacement operation. So here we have our state alpha coming in, our coherent state. We're going to hit it with what's known as a local oscillator. So this is a strong local coherent state. So this beta over root 1 minus eta, where eta is very, very close to 1. So this is a highly transmissive system. So alpha is going to come through. Most of it is going to come through. On this strong side here, most of it is also going to go through, but because it's strong, we're going to get this some reflected amount that's going to combine here for constructive interference, and it's effectively going to displace the original input state. There is an additional phase you get from this operation as well, but if tuned properly, you can neglect that. So you can, yeah, this is a displacement operation that can be done using only linear optics and this local oscillator, and it shifts your coherent state. So you can imagine just displacing it in the phasor space. Now I mentioned that these linear optic components, they perform unitary transformations, or they can perform unitary transformations on the light. And the premise of that, for clarity, is that if I have two states, say C1 or C2, both quantum states, they have some inner product. And like we saw with the coherent states, that's not necessarily 0 or 1. It can be somewhere in between. Um, what we'll see in a little bit is that I can, depending on what this overlap is, I can always find what is the minimum probability of error over which I can properly decide which one was sent to me. And we'll see in a minute where this comes from. But this is the important thing, is that if I had the optimal measurement, I would be able to decode or discriminate between these two with this probability of error. A unitary transformation transforms the Hilbert space, but preserves the inner product between these. So I perform this unitary action U, and I transform my C1 and C2 into Psi1 or Psi2. There's the action on them. And because of this property of unitaries that that they preserve the inner product, what you'll see is that the inner product is preserved. Yeah, I'm saying it's kind of circular there, but yeah, you can work out. In fact, if you know anything about unitaries, you know that this is the identity operation. So what we did though, what's important is that we preserved this inner product, and now we are operating our states. They're in a different space now. So perhaps now we've aligned them better to the measurements that are available to us. So states after unitary transformation have the same minimum error probability as before. Okay. Now, so we're going to hop back into some of the specifics related to the design of the modulation and detection. So we're going to go back to on-off keying like we saw earlier, and our depiction is getting a little bit more complicated as we move further. So we still have the 0 and the alpha, and we're going to call these hypothesis 1 and hypothesis 2. And our goal, we're not trying to send long code words yet. We're just saying, how do I determine which one was sent to me during each pulse? And you can imagine if you do direct detection, you would get some detection events, say here and here, or it will be a random distribution. But yeah, you'll get some detection events. Now, The other thing that we haven't discussed yet is that when you're sending these signals, or in this case, this hypothesis test, you need to assign a probability of how often you're going to send one or the other. Um, in this case, we'll assume they're equal priors, so I'm just as likely to send the 0 with hypothesis 1 as I am to send the alpha with hypothesis 2, so priors 1/2. I need to make a decision rule. In this case, it's the maximum likelihood decision rule. When I'm doing my photo detection, what this is saying is, okay, I get some clicks or no clicks at all. How do I decide which one I think was given to me? In this case, it's pretty easy to intuit that the right thing to do is say, okay, if I did not see any clicks, I didn't detect any photons, then I'm going to assume I was given H1. If I saw any at all, so K greater than 0, I'm going to assume that I was given H2. Um, Yeah, so the combination of the photo detection event plus the decision rule is how we define a receiver here. So we have both a detection event, which generates some output random variable. In this case, the output random variable is k. And then I have a rule that says, okay, if I get my if I get some k, what do I do with that? How do I decide what message was sent? So this is the first we've seen now a receiver defined. And we can characterize its performance in one way by looking at the average probability of error. So this probability of error is the marginal of sending either of the code words plus the conditional probability that you make the wrong decision. So in this case, it would be probability of error is the probability that I sent H1, but I guessed H2 given H1. So I guessed that I was sent this, even though I was sent H1. For those of you that aren't as familiar with probability theory, this is what this bar means. This is the conditional probability. I hope everyone here has maybe seen that somewhere. And the other way that you could get an error is if I sent H2, but I guessed that I received H1 based on my decision rule. So that's the probability of error. We can write it out more effectively here. So our 1/2 coming from the priors or from the marginal, and then the actual event based on our decision rule that would trigger this conditional probability. So probability that k is greater than 0 given H1, or the probability that k is 0 given H2. Now we're going to go to a poll question. And all of you guys help me solve how we can get the actual probability of error for the system. So what is the probability that k is greater than 0 given that H1 is transmitted? Okay, so we've got some interesting response here. So we have a mixed answer of 1/2 and e to the minus n. So the e to the minus n is going to come from the Poisson distribution. But if we think about this one a little bit more, so the correct answer is going to be 0. And the reason it's 0 is we're saying that H1 is what was transmitted to us. So we sent a vacuum state. So that's what's on the right side of the bar here. K greater than 0 means that we detected a photon. So the probability that this happens, assuming that we have this ideal direct detection, is 0. So A is the correct answer here. We'll continue then. So there's the other type of error here. The other type of error is that I sent H2 and I did not detect a photon. Now I'll go ahead and tell you that the answer to this one's not going to be A, but we'll go on to this poll then. So is it going to be B or C? Okay, there we go. 60% got it right, e to the minus n. So for those of you that don't quite see it yet, the way that we get this answer is that we know that n is the amount of energy or the number of photons present in the state that's being sent. So H2 is what's being sent to us. And we have on average n photons. If we're asking what are the odds that we don't get any photons, which comes from our decision rule here, right? So if the way that we would guess H1 is that if we got no clicks at all. So we say, okay, what's the probability that I got 0 clicks when I sent H2? And we can just plug that right into the Poisson distribution here. So make little k equal to 0. We get n to the 0 over 0 factorial. Those just go to 1, and we're left with e to the minus n. So that's the conditional probability of flipping that H2 or guessing H1 given H2. Putting this all together, then we can find that our probability of error for this pairing of modulation, on-off keying, and direct detection plus maximum likelihood decision. So this is our pairing of modulation plus receiver. This gives us a probability of error that if we work it out all the way in the end, we get 1/2 e to the minus n. So this is this is the probability of error on average. If you were to send, each of these equally many, many times, this is how often you would be wrong just making that decision. It's to say nothing about actually putting information in there for encoding. Just you're making a guess every time or a test. So now we're back to this bigger picture. We're still looking here in the center. So we've said we want to modulate. We have, in this case, really no noise. We're saying we have the exact same state and we want to detect. So we haven't weakened the state or anything. And we haven't yet said how we want to put this in coding or how we can even characterize the performance of the system when we put it into the larger information theoretic context. What we have learned is that we can use the coherent states, 0 and alpha, which is on-off keying, as the modulation format. In direct detection, so it's a photon number basis measurement plus a maximum likelihood decision rule. And that together is our receiver. And we can send and receive a single bit of information. And we found this probability of error that you'll get when you're making that decision. Now, we need to develop some context for how good this performance really is, right? Like, is this 1/2 e to the minus n that we found, is that the best we can hope to do? Is that really good? Is it really bad? So we're going to go a little bit into the theory world to try to develop this understanding of the best possible measurement. And then we'll kind of come back to this information theoretic system and then finally take us towards the full picture. But before we do that, let's see. Yeah, we're at 12:22, so for my time. So I think we're a few minutes past where I expected us to be, but we're going to take a break. What do we think, Anthony? A 10-minute break?
Yeah, maybe 10 minutes.
Okay. So yeah, 10 minutes. I don't know if I can start a timer here. Actually, I'm sure I can figure out a way to do that. But yeah, everyone come back in about 10 minutes. And if you have questions, you can put them in the chat right now too, and I should be able to address them. Well, I think probably most people are back, so we'll get started here. So, like I was saying before the break, we had developed this probability of error. Actually, I'll go back and remind us all. So we chose a modulation and we chose a receiver design, which is both a measurement and a decision rule. And we were able to understand the probability of error on average for this setup, for this hypothesis test. It was a binary state discrimination. The question that we want to ask is if I make this the more general problem of I send you two states and I allow you to change the marginal distributions, how often you're sending either of them, what's the best you could hope to achieve? And so let's picture this. So we have two states that we could send. We'll say there's psi1 and psi2. They have associated probabilities p, so the probability p that we send psi1, and then 1 minus p that we send psi2. These states, we can parameterize them inside of the Hilbert space of a single qubit. So the space here is the span of the 0 state and the 1 state. These are not 0 photon and 1 photon. This is the single qubit state. And we can make these states straddle equally the 0 line here. So they're split by this value theta, or this is parameterizing the half angle here. And then we can write them as a linear combination of the 0 and the 1 as cos theta sine theta for psi1 and cos theta minus sine theta for psi2. So if these states are orthogonal, there will be a 90-degree angle between them. They'll be, splitting the spaces of 0 and 1. If they become close to ortho or non-orthogonal, so like really, really weak coherent states, like we were saying before, then these are going to get closer and closer together. Theta is going to shrink. And so these are the two states that we're going to send, and they have some probability of being sent, but we aren't including that in the diagram here. The question that we have is, how can I choose a measurement basis? So this is these two measurement vectors, W1 and W2. They'll also be parameterized by a single angle in this qubit space. So phi is the angle. They must be orthogonal. So you can imagine that the question is really, if I give you a theta and a value of p for the priors, how do I find this angle phi that gives me the best average probability of error for discriminating between these two states? And we can solve it analytically. So we'll start out by defining this crossover error like we saw before. So the probability of measuring one, so the probability that I project into W1 given psi 2, which is going to be this function of theta and phi, and then the probability of the opposite, so 2 into 1. So now this is not symmetric like we saw earlier, right? Like when we imagined, well, I guess we'll ignore that. But yeah, this is not a symmetric thing. So these probabilities of error are different because I can move this phi angle and I can rotate these measurement vectors around the states, which remain static here. So our probability of error parameterized for the most general binary case is the probability of error is P times P selecting P2 given 1, 1 minus P, probability of selecting 1 given 2. Okay, that kind of makes sense. We're not going to go through the whole derivation here, but what you can do is you can say, okay, I can take that, I can parameterize it and find the minimum by changing this angle phi, and you get this transcendental equation, which tells you the relation between the angle phi uh, for your measurement, the angle theta for your states, and this prior probability P. So this relation is the transcendental equation is the solution. By substitution, what you end up with is this proof that the minimum probability of error for the binary case is this equation right here. 1/2 1 minus root 1 minus 4p 1 minus p sigma squared. In the case that we saw before, for the BPSK case, we'll actually simplify that even further yet. We're not going to go to BPSK. If I make the priors equal, which I would for a lot of cases in the binary case, so I make P 1/2, this simplifies, and it's 1/2 1 minus root 1 minus sigma squared. So now the probability of error is strictly a function of the inner product between my two states. And we actually saw this earlier. This is the one I showed you. This quantity is preserved uh, under unitary action. Before I move on, then, so the goal that we're going to basically get to is we want to compare how does this function, this is actually known as the Hellstrom measurement for the binary case. How does this performance compare to the receiver that we already saw and potentially a new receiver? So a lot on this slide, but right away, I want you to look at the bottom left here. So this plot is showing on the x-axis the mean photon number for our modulation for on-off keying, and then the average probability of error, which is being plotted on the y-axis. So as we are going here, we're going further and further into the lower mean photon regime. So you imagine it's harder and harder to correctly guess which one is given to us. And in the worst case scenario, we're making a true guess, so it'll be an error half the time. The red line here, this is what we saw with direct detection for on-off keying. So this probability of error for direct detection is 1/2 e to the minus n. Now these other two lines, the black line is what we just derived as the minimum for the binary case. So this is the Hellstrom measurements here. The blue line here is this Kennedy receiver, which is what's shown on the rest of the slide. So we can see this outperforms the direct detection. And what we're doing is something we've alluded to this whole time. We're taking our states here, H0 and H1, so the vacuum state and alpha, and we're doing a displacement operation. Remember, that was one of the operations we had from our beam splitters earlier. And we're going to displace it to beta and alpha plus beta, and then we're going to use our photon number measurement, which is what we have available in our toolkit. We're going to get some click. We're going to say it's either going to be 0 or 1. It's a bucket detection. We can calculate the probability of getting click given a certain hypothesis if we know beta. And so probability of getting K given H0, probability of K given H1. Since we're doing this kind of bucket detection, we can write it all out here. And we make a decision rule. So in this case, we're going to guess H0 if we don't get a click. So that makes sense because we sent the vacuum, but we've actually displaced it and we've given it a little bit of strength, but we still are going to say, okay, if we get 0 clicks, we're going to guess we were sent H1. If we get a click, if we get 0 clicks, we're going to guess we were given H0. If we get a click, we're going to guess H1. It might kind of seem unintuitive that if we give a little bit of strength to this vacuum state, that we would actually do better because now there's some probability that we're going to, get a detection event. But what we find is that the maximum a posteriori decision rule, the one we've shown here, if we write out the probability of error, so it's similar to what we saw before, but we have this 1 half 0 plus 1 half e to the minus n. This is with no displacement. If we add in the displacement, then we get this equation. 1 half 1 minus e to the minus beta squared plus 1 half e to the minus alpha plus beta squared. You can optimize this beta numerically. You can, in some situations, you can do it analytically too, but generally you can apply this Kennedy-like receiver where you have a displacement to other modulation formats, not just on-off keying. For other binary cases, you can apply a displacement beta and you can optimize this probability of error numerically, and you can find that it will generally outperform some other receivers. In this case, it outperforms direct detection. Um, and gets us not quite to, but close to the minimum probability of error for this on-off keying. Now, the thing that we are really interested in for the future of deep space comms, partly because the coherent states, like I mentioned earlier, you can use the CW laser, is to do something like BPSK modulation. So this is still a binary modulation, and you can do a Kennedy receiver on something like this too, where you can displace the minus alpha to very, very close to zero, but not exactly zero, and you can displace alpha to something like almost 2 alpha. And you'll see that that is better than exactly knowing it. So you could basically turn BPSK into on-off keying by displacing minus alpha to zero and alpha to 2 alpha. But what you'll find is that you're actually slightly better to make it not zero and not 2 alpha. So BPSK has very similar properties. We have to assign marginal probabilities to each of these. But there's another option we can do for a receiver here. Oh, and the probability of error, the minimum probability is you can actually write it out instead of as this overlap, you can write it out as e to the minus 4n. This comes from the inner product of minus alpha and alpha. So there's another receiver that's very, very similar to the Kennedy, and we don't have time to dive into the details of how it functions, but it's important to know about because it is a design for a receiver that's hypothetical receiver called the Dolinar. Uh, let's see, probability of error. Da, da, da. Okay, I'm just going to say this. Don't even bother reading it. Um, there is a receiver design very similar to the Kennedy where it applies this displacement. But as your symbol is coming through, so during the time over which you're sending this either vacuum or coherent state alpha, you are adaptively changing your displacement to try to minimize this probability of error. And it outperforms the Kennedy, but it is much more challenging to realize in a physical system. It can be done in lab experiments, but you cannot do it over the real durations that are on the nanosecond scale that happen in real communications. So it's a theoretical receiver in that sense. It was actually, so Kennedy proposed his receiver in 1973, and Dolinar proposed his in 1976. And the Dolinar receiver, what's important about it is that it does achieve the minimum probability of error. So it achieves the Hellstrom measurement for the binary case. So this is the probability of error that the Dolinar receiver achieves. And we'll be able to compare it now against other receivers that we can more easily design and build in the lab for laser communications. Okay, so now um, we we did the on-off keying plus direct detection, and we saw how we can add the Kennedy receiver into it. And we saw that the Dolinar receiver is the receiver that achieves the Hellstrom measurement for the binary case. So it's the best you can do in terms of discrimination between the binary states. Now we're going to discuss another receiver design. So we're gonna choose a different type of detection event here for BPSK specifically. You could use it for on-off keying as well, but it's really good for BPSK. Before we see the receiver design, it's going to be a homodyne receiver. We're going to remember that, okay, we have direct detection. This is performing this photon number measurement, and we get this Poisson distribution. Instead of playing with the light explicitly on the input, we're actually going to consider what happens to the random variable after we generate this. And we'll take that central limit theorem that Anthony reminded us of at the beginning of the course. So if I have my same detector right here, it's generating this photocurrent, I of t. If I apply some gain, and then this is just, straight gain being applied onto our signal. We call this I of t. I can integrate over some time and give it a scaling factor s, and I can generate a new random variable y. If this random variable, if this K is strong, or rather, if N is strong, then K actually is approximated by normal distribution. And then I can take the fact that I can scale or multiply one random variable K here and make it a new one at the output Y. So our new random variable Y is Q, G, S, and K. It will also be a normally distributed random variable where the mean is going to scale as exactly this here, right? Like QGS. So it's going to scale linearly. And then we get this like quadratic scaling with the variance. So our variance now, sigma squared, is QGS squared times N, where the N came in from the mean of K. So keep that in mind. We're going to take a strong signal here and we're going to turn it into a Gaussian distribution or a normal distribution. This is a homodyne receiver. And the way that it works is that at the top here, we have our alpha coherent state that we've been working with the whole time. So you could imagine this could also be the vacuum, or it could be minus alpha. But our goal is we want to measure the state that's coming in this upper left here. It has some mean photon number, and we know it's time 0 to t. We're going to send it into a beam splitter. So this is like the square we saw earlier. And this is also a 50-50 beam splitter or balanced beam splitter. But we're going to send in this really strong local oscillator. So it's phase matched, or we know the phase between alpha and alpha LO, and we can control that. And we send in this really strong signal here, and we mix the two states on the beam splitter. Now what we get is we get these, we'll call them like alpha plus and alpha minus. So these are two strong coherent states now in the top arm and the bottom arm. But they have different interference that's coming from them. So you can see kind of in the visualization here, these would be like alpha plus, alpha minus. We're going to put each of them onto a photodetector, and each of those is going to generate their own photocurrents. So I plus and I minus, and we are going to take the subtracted difference between those currents. So each of these I plus and I minus, they're effectively generating their own random variables, um, K plus and K minus, which are Poisson distributed. But because we're saying that we've used this strong local oscillator, and both of these have amplitude from that, this Poisson distributed random variable we can approximate via the central limit theorem as a Gaussian random variable with a mean value of n plus or n minus, depending on if it's the upper or lower arm. Then we can we take now we so we have two Gaussian random variables. We could subtract them and then do the same multiplication by the scalar here, and then we get a new random output random variable y. And this is what we're going to use our decision rule on to try to make our receiver overall. So this entire process is the detection event, and then we're going to need a decision rule to pair with this at the end. What you can show, and we're not going to go through the math of it, but what you can show is that this S is important because you can use it, you can scale this in like digital post-processing basically to scale it such that your output random variable Y is a Gaussian distributed random variable with a mean value of alpha. So depending on what this is, that will be the mean value. And um, S will allow us to create this distribution. And the variance will be 1/4. And this variance is the shot noise limit. So this is the lowest you can get from the dual photo detection event here. And so if I change this to minus alpha, I'll see a randomly distributed value around minus alpha. So yeah, we call this whole thing here the balance detector. And G is typically like built into your system or pre-designed, so you don't really have a tunability of it later, which is why we have this S parameter. But if you wanted to, you could also consider G and S to be like one tunable parameter. So I said that we need to look at our output random variable Y. So we can think about this effectively as we send in our alpha and we get an output random variable Y, which is normally distributed. I also said we can control the local oscillator. So if we assume that we know the phase value of the local oscillator, then this simplifies. The real component of this just goes to alpha. And so we have this alpha with 1/4 variance. Um, to write it out explicitly like we saw earlier, this is the Gaussian distribution centered at mu. And now we need to get our decision rule. The simplest decision rule you can kind of think about with this is if I imagine I have the BPSK modulation, so I'm sending either minus alpha or alpha. Up here, this is just saying alpha, but it could be minus alpha. I send you one of those. My random variable Y is going to give me one of these two distributions depending on which one was sent. So let's say I look at my output of my homodyne setup, and I see a random value that comes out and it's like -40. Well, that's more likely to have come from this minus alpha value. I mean, I can look at that point, I can see these two distributions and I can say, okay, that's more likely to have come from minus alpha. So the maximum likelihood decision rule is to say if y is, let's look at this. If y is less than 0, I say I was given minus alpha. And if y is greater than 0, I say I was given alpha. That's your decision rule. So now you've paired this all together. You have detection, you have a decision rule. You can calculate a probability of error for this. This probability of error will be 1/2 the complementary error function of root 2n. So this is something you can calculate. Here's the integral form of it. You can also plug this in. This is on calculators, and your computer will have a function for this in any reasonable library. This comes from the fact that we have this continuous distribution, this tail that's on the opposite side here, right? So the times that I'm going to get an error is if I guess that I was given minus alpha because I saw, let's say, like, let's call this -1. In reality, there's some probability that that could have come from the tail distribution of alpha here. So that's when I would make an error. So this system is called homodyne, and it's very practical and very useful for laser communications. It doesn't allow you to resolve QPSK because you're only measuring one quadrature, depending on how you choose your local oscillator angle. But you can imagine you can take your input light and you can, before you put it into this balance detector, you can split your coherent state that's coming in, your signal, and you can send it to two different homodyne detectors. So one with, let's say, phase 0, and then the other with a phase pi. And now you can measure both quadratures. What happens is that you get an added variance. So now you get y1 is normally distributed, we'll call it alpha real, with variance 1/2, and y2 is normally distributed alpha 2 with variance 1/2. So you get measurement of both quadratures in the phasor diagram, but you have the added cost of additional variance in your noise. Um, but it might be practical if you're trying to do like QPSK instead of BPSK. Okay, another poll question. Which of these modulation and receiver combinations is not a common pairing, or which one wouldn't really be a good pairing? PPM plus homodyne. Good stuff. Okay, we have a majority, 2/3 majority with C as the answer. Yes. Yeah, so PPM, homodyne would not really make sense. Homodyne is basically trying to measure a phase output, and PPM, you're just only sending all your signal in one time bin. So yeah, that you could do it. You would be discriminating during each pulse to say whether it was 0 or whether it was your signal. Um, you could do it, but it would not be the easiest thing to do. Just do direct detection. So good stuff. Okay. Where are we now? So a lot of the same stuff as before. We now have started to see that our choice of modulation plus detection, we can characterize it with this probability of error to see how it's performing. We still really haven't yet brought in the coding part yet, so that's going to be the next thing. But yeah, we can compare the performance, and we also know that we can define the limits for the measurement for these binary states, and you can also calculate a Hellstrom measurement for if you have more than the binary case. But um, BPSK is the one that we really think about a lot. That along with PPM. So uh, yeah, we found how we can use either the Kennedy direct detection, um, Dolinar we talked about, or we can use homodyne as different receivers that are available to us. Now we're going to move on to information theory. I think that's the last of my slides, but okay, we're going to take another quick break. Let's return at the hour, so just a quick 6-minute break, and then we'll be back, and Anthony will take over.
I was gonna answer one of these. Yeah, actually some of this is good conversation. This question has come up twice, and I kind of answered it before. Someone asked if the inner product between two states is invariant under unitaries. Why does displacement-based preprocessing improve receiver performance, and where exactly does the advantage enter, if not through changing the quantum state overlap? So let me just say this. So unitary operations, it doesn't change the overlap, so it doesn't change like the underlying information in the states, right? Due to this overlap. However, a measurement or detection is not a unitary process. Okay, that's the main thing. So measurement only extracts so much information from the state, and you want to optimize over all possible measurements. And ideally, there exists a measurement where you can extract the most information that you might want from the state. So the receiver performance is in the measurement itself, which is not unitary process. That's what I would say. Someone also asked this interesting question, and I kind of answered it. Jack, maybe you know a little bit more about this. Someone asked, I was thinking what would happen if you add a squeeze state. I would like to hear
Mhm.
your opinion. And then they also just now asked, can we use thermal states? I answered this squeeze state. I just came up with this randomly, but it seems like this is actually an interesting question. I
Yeah,
told them you could
let me share
use,
my screen again for that. That's actually a really good question.
yeah. So let me answer this just real quick because I want to get your opinion also. Because I said you could do because it seems like you could just do like a BPSK, but with a coherent squeeze state plus homodyne.
Yes.
And
Yep.
so then you reduce, you get this probability of error, which is from homodyne. Yeah, that 1/4 factor there, that's
Yep.
all coming from shot noise. So if you
Yep.
just squeeze it, not you increase that or reduce that probability of error in your modulation scheme. So that's one
Exactly.
thing that I said just sort of on the spot, but I'm sure there's a lot more literature and research behind that.
Yeah, I mean there's a whole host of things you can start to do if you don't limit yourself to just the classical quantum communication channel that we're talking about here. If you want to say do other things, like we've actually been on a project, or I've been on one, where you're still trying to do so this research project, it's called Quanet. You can go look it up. It's a DARPA project. But basically the goal is, okay, if you're going to modulate light like this over a fiber, we're not even going to talk about like free space links yet, just over fiber. And I want to be able to tell when someone has tapped this fiber, for example, or some, other party is attacking us in some way, that basically they're making a change to our modulation. If you add on an additional really small amount of squeezing on top of this, like Anthony said, you can change the variance of what you're looking at. And actually, the variance is more sensitive to small changes in the system than the mean value is. So it gives you an additional benefit, not necessarily in capacity, but basically you can keep the same capacity, but give yourself additional security guarantees on top of it. That would also apply in free space systems as well. And there are things you can look at, like you can do things like quantum data locking or look at wiretap slash like eavesdropper channels in free space. So yeah, it's a really good question. It's a really open question, I would say. I don't think anyone can give you an exhaustive list of why squeezing will benefit you in some, communications programs or others. But certainly there are known applications where it can give you a benefit, either in reducing the noise of your measurements or in providing additional capabilities on top of your classical communications. So
I
hopefully that,
guess if
yeah.
if it's not going to change the capacity, obviously, but I guess if you wanted to have an unreliable rate, so you're sending, messages, but with some tolerance for the error, I guess it'll reduce the error. But again, your messages will still be
Mhm.
error prone, but your error probability will be lower, not
Mhm.
not to zero, but lower. Right.
Yeah. Okay. Cool. So I think we are back from the break. Did we get all the questions? Yes. Okay, cool. Anthony, I think we're on your slides now, correct?
Okay. Yep. Yeah, we are.
Okay, and I'll take over the Q&A.
Great. Okay, so let me try to minimize absolutely everything, hide everything, hide floating meeting controls. Thank you. Slideshow, play from current slide. Okay, so we're going to jump into a little bit of classical information theory. Again, we're someone asked about qubits and entanglement and all this stuff earlier. I want to clarify again. So we're not dealing with quantum communication. We're not sending qubits over channels. What we're really doing is taking classical information and encoding it into these quantum optical state, like a coherent state. It's really a semi-classical state. and then sending that state over a communication
The
channel.
I'll just step in one thing on this. That question might be arising from when I discussed the derivation of the Hellstrom limit effectively for the BPSK
Oh, okay.
case, because I did say we're putting these states in the span of a qubit. You can think
Uh,
about the states, think about BPSK still, again, for an example. You can think about that as a state in the span of two qubits, but not literally itself being a qubit. The coherent
yeah.
states are in a bosonic mode, so they are not in a discrete fermionic system like a qubit would be. So they actually, because they have the representation over the infinite Fock basis, they're bosonic inherently. But yeah, you can treat them in some ways like qubits. Um, Hopefully that helps.
Yeah. Yeah, and again, these are not orthogonal states themselves, so they don't you have to be a little bit careful there. Okay, so yeah, so we're gonna talk a bit about classical information theory and information channels and capacities, communication rates, things like that. And then we're going to move on to a little bit of quantum with these so-called joint detection receivers, where we see even more benefits from using optimal and in that case collective measurements on a bunch of symbols that you receive. So what is an information channel? So an information channel or sometimes a communication system. Basically what it turns source messages into code words, like from this modulation scheme that we have, for example, and it sends them through a noisy channel. And then on the receiver side, we attain some some message, and we try to decode that message with small error and get some estimate of what was actually sent. So in our case, what we've been typically considering is we have some physical, or not some physical, but some binary message. And I'll just try to draw this really badly, but that's okay. We have some modulation scheme. So this is actually our information channel in most cases. You know, in some cases we've been considering only the modulation itself as the physical source of error. And we'll have I'll denote a channel by this curly N. This might be the physical noise channel, like a lossy, free space channel. And then we have the detection or receiver side. And this is our physical information channel in most cases. And from the detector, we get some guess of what the source message is. So this is kind of like a classical to classical channel, but there's some, a little bit of quantum business happening at these stages, whether that be in the detector. We're encoding or modulating in a quantum system. For example, the binary uh, phase shift keying, so coherent states that introduces noise, so that will lead us to this noisy information channel. And then there's noise in the channel itself. Okay. And so generally, though, we can describe this, at least in classical information context, by this probability transition matrix. If there's many different messages and many different things on the receiving side, and this will be some conditional probability. So the probability of a message being received, Y, given that the message sent was X. Okay. So that describes an information channel or a communication system. Um, Let me just say this also. So I'll say this verbatim. I have some notes here. So in classical information, so the measurement is somewhat implicit because all the messages that you encode and the things that you receive are classical. So you don't really do this optimization over all possible measurements, at least in principle. However, in optical communication, right? So this is this modulation scheme or these physical schemes. The channel is inherently quantum, before detection. So different receivers actually induce different classical channels, and we saw this. Even when we ignore, oops, sorry about that. Even when we completely ignore this the like a physical noise, we saw that the modulation scheme together with a particular detector gives us various P's, right? So we had the homodine, we had Kennedy, we had Dolinar, things like that. So just the modulation and the detection scheme will give us various um, noise probabilities. Okay, so let's move on. So a simple example, very common, paradigmatic example of a um, of a noisy channel is the binary symmetric channel. So we have two messages. So it's like we're trying to send a bit, either 0 or 1. Here it says 1 or 2. Um, so the binary symmetric channel, it's just a bit flip channel with some probability P. Okay. So let's say I want to send 1, but with some probability P, it gets flipped to 2 and vice versa for 2. Okay. And then for some other probability, 1 minus P, I get what I sent in, right? And the probability matrix has this simple form over here that just compresses everything very nicely. So we say that if the probability is at the extrema points, either 0 or 1, then 1 bit can be sent reliably per channel use. And why is it reliably? Obviously, for p equals 0, this is it's clear that it's reliable, right? There is no noise, and 1 goes to 1. But it's also reliable for p equals 1. And you say, well, an error occurred. That's true, but we know precisely what happened, right? We know that 1 went to 2, and we know that every single time with certainty. So reliable here means that there's no uncertainty in my received message given my input. I know that even for p equals 1, I know that every time I receive 2, the message that was sent was 1. So that's what we mean by reliable. However, for all p-values in between, we're generally uncertain on the receiving side about what was sent. And in the case of a fair flip, so p equals 1/2, we can't send things reliably at all, right? On the receiver side, if I get 2, I have no idea whether 1 or 2 was sent, right? It's equally likely, equally likely that they were both sent. So a natural question is in general, how many bits can be sent reliably per channel use? And that is leads us to, oh, well, we'll get to that'll lead us to the so-called communication rates and Claude Shannon's channel coding theorem. But first, let's just see a physical example on this and tie it back to what optical communications. So BPSK modulation and receiver. So for the BPSK modulation, the source symbol here is, the raw symbols are x equals 1 and x equals 2. The source symbols are then we encode 1 into plus alpha and 2 into minus alpha. So this is the modulation scheme, which really, in the case of no loss, completely determines this information channel, this probability matrix. And then at the output, we guess alpha or minus alpha, right? And this guess is really determined by our detector, right? So we have a modulation scheme which determines in part this transition probability matrix, and also a receiver design, right? So the examples given right here are Dolinar or Homotdyne, and the modulation together with the receiver induces this binary symmetric channel with different error probabilities, right? So for Dolinar, we know that the minimal error probability is achieved for Dolinar, and it's given by this is the Hellstrom limit. And for Homodine, it's given by this case. So we see explicitly that without any inherent noise, like additive Gaussian noise or loss, we still get errors due to the physical modulation. And these are actually, in some sense, these are completely like due to quantum effects and this overlap between alpha and minus alpha being non-zero. I mean, we see in the high power limit, for example, that these go to zero. I mean, this is clear from the Holmerdine case, because alpha, this overlap is completely due to shot noise fluctuations. And yeah, so cool. That's a physical realization of a binary symmetric channel just from the modulation and receiver. Okay. So how do we quantify uncertainty? Well, Shannon introduced this so-called Shannon entropy of a random variable, which quantifies the amount of uncertainty, average amount of uncertainty, sometimes called the surprisal, by revealing the value of a single instance X. Let's see here my notes. Yeah, so this is so-called Shannon entropy for a binary for a binary valued random variable. It takes this form, okay, and then generally though it can be written in this way. This is the Shannon entropy formula. It's just the sum of these pi's, and this is this quantity log 2 of pi is sometimes called the surprisal. So how surprised would you be if you were given a system? And this is the average surprisal. So there's this famous thing. So this is called the Shannon entropy. Entropy also arises in physics and statistical mechanics. And there's this famous back and forth between Shannon and Johnny von Neumann, one of the forefathers of computation, theory of computation. And von Neumann told Shannon to call it entropy because no one knows what entropy really is. So he'll have an advantage in all the conversations. So this information quantity is called the Shannon entropy. And it looks a lot like Boltzmann's entropy and quantum entropy if you know quantum mechanics. Okay. And here is the plot of the binary entropy. It has a peak value at 1/2. Again, you'd be like you learn the most about the system. This is really the information content. You learn most about the system if the coin is, a fair coin. Like for example, if I give you if we flipped a coin and it went to heads, you'd be most surprised by the outcome because you weren't sure what the outcome would be prior to the flip. However, on completely unfair uh, coins. Like this would be if I didn't flip it at zero, would be like if I didn't flip it at all, right? And I just said this is heads. Of course, you wouldn't be surprised whatsoever. And on the other side, if it was completely an unfair coin, so every time I flipped it, um, let's say it went to tails or something, then you wouldn't be surprised. So this is a measure of surprisal or the information content in the system. Okay, so we'll need to go on to mutual information, which is like a measure of total information of X given Y. But first, we have to talk about a few things. Um, we won't really use this, but this is a joint entropy between two random variables, X1 and X2. So just like we can have joint probabilities, we can have joint entropies. One thing that more likely comes up here is actually the notion of a conditional entropy. So, say for example that we have a random variable x2 with a certain realization into. This is how surprised would you be about getting x1 given that you know x2. All right. So obviously, if these things, if x1 and x2 are correlated, then you learn a little bit about x1 first by measuring x2, right? If they're completely uncorrelated, then that wouldn't be the case. And so then this total of the two random variables is just the conditional entropy is just the average amount of uncertainty resolved by revealing the value of x1 if x2 is known, right? And it's just this average value. Again, if let's say if the joint probability distribution, let me write this terribly, x1, if these are completely disjoint, I'll just say P1, P2, that makes things easier. Then H x1, x2 equals to h of x1. Oh, hopefully you can read that. Sorry. So if these are completely disjoint random variables, like completely independent, then obviously learning anything about x2 will not give me any information about x1. Okay. So it's a measure of relative information. Given one variable, how much can we learn about the other? This leads to the so-called mutual information between variables x1 and x2. So this is the amount of the information content of x minus the information content of x given that we know y. Okay. And this is physically, this is the amount of information y can convey about x. Again, if x is independent of y, then we have this, and the mutual information is 0. So, in other words, then we learn nothing about x given y, and this is important. And I keep drawing everywhere. This is important for communication. Here we're talking generically about random variables, but for the communication, the information channels, we'll have some information channel. Maybe I'll call it squirrely Y, so don't confuse it with the mutual information. So this is an information channel Y, and hopefully, if X is our message and our transmitted message, the message that we want to transmit over this information channel, and Y is the received message. Hopefully, the mutual information is non-zero because we want to convey some information about X given the received message, right? Okay, let me get off that. Let me take a quick look at my notes here. Oh, there's one other interesting thing, and I just wanted to say this. I don't have this in the notes, but I do want to say it regardless. Um, one thing that the mutual information obeys is this so-called data processing inequality, which is nice to know. So I'll just put this as a side note. So if we have this so-called Markov chain where like Z is independent of X, but it could depend on Y. So this Z could be like, this is X is our transmitted message, Y is our received message, and Z is like some processing that we do on the back end. Then in general, we had the following data processing inequality, um, which is useful and used a lot in mathematical proofs and for physical intuition. So all this says is that extra post processing, extra processing on the back end doesn't increase our information content about X, the extra information that we can receive. Okay, cool. Right. Channel coding theorem. Fantastic. So let me just do a quick look at my notes here. Yeah. All right. So channel coding theorem, sometimes known as Shannon's second theorem or as capacity theorem. Um, so for a classical channel, so here we have again this information channel, and we're going to assume that we have n instances of it, so n uses of it, right? And we're going to assume that each use is statistically independent and identical, so this IID assumption, okay? And it turns out that the number of bits that can be faithfully sent over this n uses of the channel, and what I mean faithfully, because this is actually important. So this assumption of faithfully means that the probability of error goes to 0 as the number of channel uses goes to infinity. So we want 0 error, faithful, reliable communication over this channel. Right? I want to know definitely what the message was sent. I want to know definitely what it was. So the number of bits that can be communicated faithfully over a channel is N times C, or C is this so-called Shannon capacity, or just the capacity or channel capacity. So again, reliable is this P, this error probability goes to 0, where N is the number of independent channel uses, and C is the channel capacity. So this is the upper bound on the achievable information rate, which is bits per use of the channel. So mathematically, if I say that I can transmit k bits over n uses of a channel. So this is the rate equals k over n. So k is the number of bits over n uses of the channel. If I say that I can send this rate reliably with zero error, then it is always less than or equal to the channel capacity C. Likewise, if I have an R, if I say I have an R that's greater than C, um, then this is unreliable communication. Then necessarily this has some probability of error associated with it that doesn't vanish in this large channel uses instance. So just an example from our modulation schemes. So from this BPSK, for instance, that we have, where we say 0, 1 is really, we're just doing this one-to-one encoding, plus or minus alpha. Where are you at? Alpha. BPSK plus or minus alpha. Actually, here we have n equals k. So we just have a unit rate channel, and we have an error probability p, which is some function of the of alpha squared of the me photon number, generally for all these different types of receivers. Right. So we always have an error prob. This is a unit rate encoding, this modulation scheme, and there's always an error probability. So actually, to get a vanishing error probability, we'd have to go to a larger alphabet, or a bigger. We'd have to do like one of these codes, an actual code, in order to get a vanishing error probability. So here we can make the error probability small in our BPSK and everything else by increasing the, like, a physical quantity, the power, though that's not always possible. So, you might want to do both in physical communication setup, high power and also actual code words to get
Anthony,
over.
I accidentally just clicked answer live for a question in the chat that I should have answered, but I can't reply to it now. The question was, what is little k?
Oh, little k is like, so it's like a message that you want to send. So it's like the number of bits, so yeah. So it's just the number of bits that you want to send, right? I mean, I could send 1 bit, and so either 0 or 1, and that would be k equals 1, or I could send a 2-bit message or a 3-bit message, etc. And so I want to send maybe a k-bit message. So this is like k bits. So maybe this is like a message in binary encoding. Maybe this is like a 0, 1, 0 or something like that. But actually, what I might want to do is encode this into a larger, so this is k up here. So it's the number of bits that I actually want to send, but I might encode it into a large block of n. And we haven't really talked about codes too much here, but this comes up in reliable communication, that you actually may want to do redundantly encode a 010 into a much larger code block, like a 000111000 is equal to 010. And so k is the actual, number of bits that I want to send, and n is some larger code block. And yeah. So this is about efficiency of this encoding and the maximal reliable rate that you can achieve. Hopefully that answers. Okay. Moving on. So again, going back to this example of a binary symmetric channel, which applies to our BPSK modulation schemes and others. So in this case, again, we have this binary symmetric channel. Um, I don't know why there's all these Q's and P's. So P is 1 minus Q, or Q is 1 minus P, however you want to write it. In any case, we have a bit flip occurring with probability P, and everything stays the same with probability 1 minus P. You can compute the Shannon capacity. Oh, one thing I did not mention. Oops, went the wrong way here. One thing I did not mention. Let me erase all ink on slide. I did not explain this. So I said that this is the amount of information. Um, yeah, so the mutual information is the amount of information about X that you can convey from Y, right? But we also have a max here for the probability distribution of X. So this is like, I mean, and some this is we're sort of maximizing over all possible things that this alphabet could be, and this is really a statement about the channel. Okay, so this is really about the statement of the channel itself, and not of the source symbols, right? So let me just make that clear. Right. So Shannon capacity of the binary symmetric channel is just given by this. So this formula down here, 1 minus the the binary Shannon entropy. So if you recall, this binary Shannon entropy. Let me just actually write it like this. I'll like this better because this is just the easiest way to write things. There has to be a negative because this quantity is positive, and there's a log base 2 of a less than 1 quantity in the log. So that has to be a negative. So pi P1 is equal to P, and P2 is equal to 1 minus P. So that's the binary. I mean, this formula right here is general Shannon entropy, but for the binary case, P1 is P, and then P2 is just 1 minus P because of sum of probabilities equals 1. So for this binary symmetric channel, we get this formula, and we see immediately, if you recall, the binary entropy can be, it goes between 0 and 1, and so this is strictly less than 1 and strictly greater than equal to 0. Remember, this is bits per channel use, so it's between 1 and 0. Okay, cool. Physical example again. Let me clear all these drawings. Physical example is this BPSK modulation, and given some receiver design, we saw this a bit ago. That given our modulation scheme and the receiver design, either Dolinar or homodyne, this induces a binary symmetric channel, and the receiver really tells us what the what the error rate is for Dolinar receiver. This is this is the Hellstrom limit, and then for homodyne, it takes on this value. And recall, so again, the Shannon capacity here is the bits per transmitted BPSK symbol. This is the maximal bits per transmitted BPSK symbol. Okay, so poll question. Great. So is the classical Shannon capacity, so C, is it an achievable rate in principle? Hopefully I said this, but it's known as Shannon's channel coding theorem. So is this an actual achievable rate in principle? Like, can we set up a scheme that actually achieves the Shannon capacity? So we'll give you just a minute here to answer that. Okay, I think we can, yeah, great. So 50-50. Oh, that's exactly 50-50. Cool. Well, maybe not so cool. I'm not sure. But actually, so the answer is actually yes. So this is surprising. So Maybe that's good though. So you learned something today. So the the classical Shannon capacity is actually is an achievable rate, and that's what makes the channel coding theorem so powerful. Is that Shannon showed that this is an upper bound to the physical communication rate, but also that there at least exists, so you give an existence proof that this capacity is achievable by some scheme. It might be hard to, one, come up with a scheme given a channel that actually achieves it, and two, even harder to implement it in practice. But at least there exists one in principle that will achieve the Shannon capacity. So actually, the answer is yes. In principle, the Shannon capacity is achievable. Let me turn my pen off. Oops. Man, we're really going far here. Oh my God, wrong buttons. Okay, fantastic. Um, so what determines a noisy channel? So we mentioned, so let's go back to this setup from the very beginning, in fact. So we have a message, right? So a physical message that we want to send. We encode it in this binary encoding. And then we do so in some sense, this is really, we'll say that this is X. This raw binary data is X. And then we have some modulation scheme. So we put it into some quantum state. There's a physical noise. We get a noisy state, and we try to do some detection and decoding at the receiver end. So all of these things really determine the noisy channel. So the choice of modulation, the actual transmission through a medium such as a fiber optics or free space, and the receiver determines the information channel here. Okay. So again, so going back to our BPSK, this is our raw binary symbol. Everything in here is the information channel, right? And so this is our modulation scheme. So this BPSK modulation, either plus or minus alpha. We send plus or minus alpha through a uh, lossy channel, so photons get lost. Again, nice thing about coherent states is all this does is you maintain a pure coherent state, but it attenuates the power in the coherent state by some factor eta. And then and then on the receiver side, we have either a Dolinar or Homodyne or some other receiver. And then at the output, we have this guess Y. So all of this in this box is really the information channel and leads to this, well, at least in this case, information channel, which is the binary symmetric channel. Okay, so all of these layers really really describe your information channel. And for instance, in this case, again, since a lossy channel just maps coherent states, but with an extra attenuation factor, Dolinar or Homodyne just change by these prefactors in these exponents, right? So, but you can think about this in sort of two steps, which is interesting to think about. So there's really kind of two levels of noise here that go on that determines the noisy information channel. So one is some sort of is like a quantum noise, and this is due to the non-zero overlap between coherent states, right? But in this binary, that this BPSK modulation scheme. So there's an inherent noise just into our modulation itself, right? And this is most prevalent when we choose a receiver. So Dolinar is at the Hellstrom limit, so this is the minimal error probability that we can get. So no matter what, we at least have some error probability, and that's just purely due to this modulation scheme. And then the second again is this is the physical noise through the medium, to the transmission medium. And this is an attenuation. It's like a shrinkage in phase space due to attenuation that brings these these modulation words, these code words, physical code words closer together. This is just some plots just to show you a difference between capacity and this error probability. We saw these from before, the Homodyne and Kennedy, and this minimum error probability, which is achieved by, I keep doing that. sorry. With this minimum error probability, this Hellstrom limit, which is achieved by the Dolinar. And so we see some, Dolinar does really good. Kennedy does pretty good too. Homodon does really good compared to relative to the Dolinar. But there's maybe some crossover behavior between Kennedy and Homodine. But again, the probability of error here actually differs a bit by the capacity. So this is the capacity bits per BPSK symbol. So in this BPSK modulation, Dolinar is the highest, clearly, and then Kennedy and Homodine in between, but notice there's no crossover. So there's some a little bit of differences between the capacity and then the error probability, even though they are related. Okay, so that's all of classical information theory. And purely classical information theory, we're now going to add just a little bit of quantum by thinking about measurements and as quantum measurements, right? And this is where things get a bit different. So we've already seen a bit of this before. So we introduced the Shannon entropy. Now we're going to introduce the von Neumann entropy. And so how is that defined? So first of all, we're going to introduce a density operator. So density operator is a generalization of a quantum state. So for a pure state, the density operator is just a ket-bra. It's just like this. So it's a matrix and not a vector, right? So let's suppose we have a mixture of pure states. So this is sometimes called an ensemble. So we'll just write it like that. This is an ensemble where these PKs are probabilities. And the psi of k's are not necessarily orthogonal. So there's just a mixture. This is a convex combination of pure quantum states is technically what it is. Okay. And then the density operator for this ensemble is just a sum of a sum like this, right? So I'm giving you I'm randomly sending you a state psi k with probability p of k, right? So it's like I have some source that randomly spits out quantum states at with probability p of k. So this would be like having a BPSK modulation scheme and randomly getting sent plus or minus alpha, right? So this is like that. So there's some properties of the density operator which it necessarily must satisfy in order to be a good quantum state. It's really just a statement about probabilities, where the sum of probabilities is one. Each one of the diagonals of this density operator or the eigenvalues is greater than zero and are real. And so really what this says is that, for example, we can always do this diagonalization of the density operator. This is the diagonalization where now these W's are orthogonal. So this is just a matrix. So we diagonalize it with its eigenvectors. And all of these statements above together all these statements above imply that lambda I is actually just a probability distribution. Is a discrete probability distribution. You could do this in continuous variables as well. So yeah, you can do this in continuous variables as well. So the eigenvalues are actually just probabilities. So the von Neumann entropy actually in this case is then the von Neumann entropy of a quantum state is really just the Shannon entropy of the eigenvalues, right? And so the von Neumann entropy of a pure state is actually zero. So this might be a little odd. It's like, quantum states have some inherent uncertainty about them, right? So psi could be like a sum of different pure states, right? But its entropy is zero if it itself is a pure state. And so there's some inherent uncertainty or probability quantum uncertainty in the state itself. But the von Neumann entropy of a pure state is zero. It's kind of like, maybe there's some quantum uncertainty in the state, but I know what state is sent. Okay, so you can think of it that way. Entropy of a pure state zero. Let me switch to my thing. There we go. Okay, So now we get into a little bit of tricky stuff. So now we're gonna talk about this Halevo capacity. This is also this accessible information, and it's going a little bit beyond the at least the classical standard receiver capacity that we discussed before. So let me say a few things first. So I'm going to try to be as coherent as possible. So Shannon, the classical Shannon capacity, Shannon capacity C um, um, is really a statement about in uses of a channel. Um, so let me write it this way. So we're going to define C1 as classical Shannon capacity from one use of an information channel, right? And now it turns out that for at least classical capacity in purely classical theory, um, if we have n uses of this information channel, then the classical capacity is actually just n times the Shannon capacity from before. Okay, so the C1 is the information rate, is the upper bound of achievable information rate per use of the channel. So we see here explicitly that's exactly what this is. All right, and the reason being is that so this is actually a per symbol item. So what I mean by per symbol is I'm sending symbols over this information channel. I'm measuring. I'm sending symbols over this information channel, and I'm measuring. Okay, so there's two levels uh, which might occur when we go to the quantum theory, and that makes things very tricky. So for one, in the quantum theory, I could in principle, we're not going to get into this because that makes things very complicated, but I could do one thing. I could actually use entangled code words. All right. So that makes things already challenging because now it's like yeah. So then at the receiving side, in general, my received messages will also be entangled. So clearly, this strict additivity over here, this is called additivity of the classical capacity. This additivity won't hold from that end alone. We won't get into that here, so we don't have to deal with that. However, an extra thing that we can do, and we mentioned this before in a different context, but measurements are very important. Measurements are very important, especially in the quantum theory, when we have physical encodings of digital information. So what we could actually do is instead of having these independent receivers on the detection side, we could actually collect all the uses um, of these information channels and do a joint detection, which combines them maybe cleverly with unitaries and then does a joint detection scheme on all of these uses. Okay. And so in general, this leads to this so-called Halevo capacity, which is actually sets, so let me write this in blue beside the Shannon. This actually sets so C1 here now is the classical Shannon. So it's I'm using, I'm measuring symbols as they arrive one at a time independently. This leads to this notion of the Halevo capacity, also sometimes known as the accessible information, by allowing for joint detection receivers, sometimes called entangled measurements, but allowing for joint detection receivers. And this can allow you to go beyond the classical Shannon capacity. And some sense, so I mentioned before that this is additivity. This is called super additivity. There's different notions of superadditivity in the literature, so I'm going to describe this as measurement-induced superadditivity. It's really due to these joint detection receivers on the measurement side. And what's quite nice is that this Halevo capacity is actually achievable. This is written in this so-called HSW by Halevo, Schumacher, and Westmoreland. So this HSW theorem is that the Halevo capacity is achievable. So after all that running about, what is actually the Halevo capacity? So for our cases, for example, this BPSK modulation, where we're sending these BPSK symbols, which are pure states, that the Halevo capacity is actually just the von Neumann entropy of the ensemble. So remember, the ensemble is just PK psi k for pure states. Um, Psi k. And so the average state in this case is just PK psi k. Psi k. And so the Halevo capacity is then actually just the entropy of this ensemble average state rho, and then take a maximum over all the, it's kind of like probably ways I could the probability distribution that I could send it in. This is similar to the maximization over P of X in the mutual information for the Shannon capacity. So if you do this, you can prove that the Halevo capacity takes some value that depends on the overlap between these two states. And so if the two states are orthogonal, this is 0, and the Halevo capacity is maximal. This is like a P equals at P. Recall that for binary entropy, P equals 1/2 is the maximal Halevo capacity. I mean, is the maximal point for the binary entropy. And at sigma equals 1, so basically these code words are getting very, 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 very close. So the overlap is approaching 1. This goes to 0. Okay, great. So that's a little spiel on the Halevo capacity for pure state. Okay, so just to write these things out explicitly, so so again, capacity of a so that we have this binary capacity. So let me see. Yeah, so I mentioned before that the Shannon capacity, this is the let me this up here is the Shannon capacity symbol by symbol. So this is the purely classical Shannon capacity. It's just 1 minus the binary entropy. Here, this is binary entropy of P, where P is the probability of error. For our pure state alphabet, P is just given by this. Recall this was this error probability. Darn it. This is the error probability. So this is the Shannon symbol by symbol Shannon capacity for a binary symbol. The Halevo capacity we just argued takes this form. And so if we just plot these as a function of sigma here, then we see that the Halevo capacity is always larger than the Shannon capacity. And what's interesting is that as sigma approaches 1, so recall sigma is the overlap between two states. We'll assume it's a real value. So sigma is the overlap between two states. As sigma approaches 1, so these two states become very, very close. So recall, like in binary and BPSK, plus or minus alpha, if these states get attenuated, they become closer and closer in phase space. So sigma approaches 1. Interestingly, the ratio of, well, first of all, both the Halevo and the Shannon go to 0, sigma approaches 1. However, there's much more information content in the Halevo capacity than in the Shannon capacity because this ratio goes to infinity. So this suggests that doing not symbol by symbol detection, but a joint detection is informationally rich. And this again points to the fact that quantum measurement is a resource for communication. Great. What else do we got here? Next. Cool. Just to reiterate this point with the BPSK modulation, um, recall the BPSK modulation, the overlap takes this explicit form in terms of the mean photon number, e to the minus 2n. And we can plot, depending on how we plot it. So here on the left, we plot the capacities versus the mean photon number n. And we see the high-level capacity here and all these other different types of rates, information rates for the different receiver designs. Dolinar is the Shannon, it achieves the Shannon capacity, right? So that's why Dolinar here is C1 and the Halevo is way over here, whereas we have Kennedy and Homodyne and also this USD, which I don't think we really talked about, so I won't get into that. So right. And we could also plot it against, this is the same plot from before, from the previous slide. We can also plot it against sigma for all these different receivers. And so we see that Halevo capacity can actually get you a pretty good benefit for um, um, over the symbol by symbol detection. And again, it's not really shown here, but the difference between C infinity and C1 is very large in this low photon number regime, or as sigma goes to 1. So that's n goes to 0, right? So in the low photon number regime, you can get a large benefit relative to the Shannon symbol by symbol capacity. So this actually, yeah, this is probably the best way to see that is to define the so-called photon information efficiency. So we want the most information per photon in our modulation scheme. So here again, n is the mean photon number per mode. So we see that for small number of photons, the Shannon capacity and all these other information rates associated with these different receiver designs, they plateau for a small n. So that what this actually means is that um, C1 of n is 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 order n, so it's linear in the photon number. So for n much less than 1, right? Because again, this is bits per photon, so this is C over n, and this plateaus to constant value. So that means that these capacities are order n and then decay, right? So the capacity goes to zeros and goes to 0, clearly. However, the Halevo capacity actually blows up as n goes to 0, and that's because uh, of the following. Actually, and maybe hopefully I'm saying this properly, Jack. But as far as I know, this is actually because um, this is not a linear in function clearly, but actually it goes something like um, log 1 over n. And so as n gets very small, you get this blow up.
It's log of log.
Oh yeah, yeah. There you go. Thanks, Jack. Log of log. Is that just is that for Halevo or is that just for the
It's the leading term for both that and the
Okay.
envelope
Okay.
of,
Okay.
yeah.
Yeah. Oh yeah, right. They have the same slope. They have right, right. They have the same growth, but different prefactors for the slope. Okay, so yeah. So that's so you do get this leading order like in prefactor, however, you get this other term that blows up like 1 over n as n goes to obviously, and absolute rate, n goes to 0 faster than this term blows up. So the absolute rate goes to 0 as n goes to 0. But the bits per photon, the information content, is very high for these Halevo capacities. So whenever you have in low photon number or photon starved regimes like deep space or very low power symbols, achieving the Halevo capacity, it's kind of a big deal. Next. Ah, okay, cool. Whole question. I think there's only this one and one more. So stay awake. So in which regime is quantum? So like quantum, when I mean quantum here, I mean joint detection, these types of things, most likely to provide a qualitative advantage over classical communication strategies. And what I mean by classical, I mean symbol by symbol or these local measurements. Um, which, could change what communication rates are achievable in principle. So do we expect from these plots and the discussion, do we expect high power signals, so many photons per mode? Do we expect quantum to provide an advantage here? And signal starved regimes, so where we have much less than one photon, both regimes equally, or neither quantum effects only modify prefactors, not really any fundamental scaling type of limits. So we'll give you about 60 seconds to think about that. Okay, I think we can probably close the poll now. Great. So most people, about 60% of people said signal starved regimes, much less than one photon per mode. Yeah, so for at least the task that we're talking about, where we do, classical to quantum communication, yeah, signal starved regimes are sort of where we see the most benefit, particularly in this Halevo capacity versus classical Shannon capacity. Great.
Awesome.
Oh,
And
fantastic. So yeah, we'll move on from information theory, formal, and get a little more physical with Jack here.
yeah, so I know we're closing in at the end here, guys. It's been a long one. I only have like 8 slides left, so we're not going to take a break. We're going to try and go through them and get done a little bit early. So Anthony, if you stop sharing, yep, I will take over. Do share, share that. Okay. All right. So yeah, we're gonna continue right on here. Joint detection. I wanted to provide another visualization of a way to think about joint detection to kind of contextualize in the receiver side what it is that we're really doing. So, as Anthony said, the Halevo-Schumacher-Westmoreland theorem provides an upper bound in the capacity when we allow for any quantum measurement. There's this explicit gap that he showed between the capacity of symbol by symbol and the Halevo for coherent detection. So there's this upper bound. Um, and joint detection is what allows us to achieve this super additive capacity, surpassing the C1. So we've got the definitions in the lower left here, but to visualize kind of what's going on, imagine I send you one of these code words. So we have the coherent states that we've talked about this whole time, and we have BPSK modulation. Notice that each time bin is going from 0 to tau. So it's a total of 8 tau for this. And in what we saw earlier, we would imagine, okay, well, let's just choose what was the best symbol by symbol measurement we had, the Hellstrom measurement. We have the Dolan in our receiver. Even in its theoretical design, let's deploy that. During each of these symbols, I'm going to get some random variable outcome y1 all the way up to y8. And I am going to, in some way, I'll have some decision rule that pairs with this, that I can make a collective estimate based on my individual 8 random variables of what my message was that was sent, right? So I sent this code word. This is actually a Hadamard code word. And if I do this, the capacity of which I can send information would, in the upper bound, be CN. In fact, if I limit myself to this code word, it technically is lower. But with BPSK modulation, I could upper bound it to this, or sorry, C1, C1. This would be the symbol by symbol capacity. So that's what I get. I still sent it over 8 time bins, but I have this symbol by symbol capacity. The joint measurement would be, okay, I take all of these symbols together. I'm performing a single measurement on all of these. So I'm going to call this set of possible measurements, this set pi j from 1 to m. So there's m possible outcomes. Um, and I get one outcome y from that. So I perform one measurement on all this. This channel induced by this modulation and this measurement setup gives me my C8, we'll call it. Now, technically, I haven't told you what this measurement is or how to do it optimally, but let's just say there is one, and we don't know how to find it, but there is one, and that gives me this C8. And so now I can show that this joint detection provides me an advantage by taking this C8, or generally CN, normalizing it to the number of channel uses that I had to use to perform this operation, and compare it, and you'll see that there is this super additive capacity on the receiver side that exceeds one, right? So this joint detection exceeds the symbol by symbol capacity. Oh, sorry, let me also put my laser back on. There we go. Okay, so I didn't tell you how to construct anything that can perform a joint measurement. I just told you that there are one. There are some. The only structured joint detection receiver that allows you to scale to an indefinitely large size is known as the optical green machine. So this was proposed in 2011 by Saikat Guha, who taught some of the classes, one of the classes yesterday. He's also the director for the CQN. He proposed this in 2011, and he looks at a system where you take the Hadamard code words, exactly like the ones we were just looking at in the slide before. So this one that's highlighted here, that's what we were just looking at. And you perform a unitary operation, in this case, a Hadamard-Walsh transformation, and you take your input Hadamard BPSK codebook and transform it into a pulse position modulation codebook effectively. It's like a transformation of your codebook in its entirety. All the energy is compressed. So now all of my signal is sitting in one of these time bins. And then if I pair it with direct detection, then I can calculate my transition probability matrix. So I have my input X, which in this case would be M random variables, and here specifically it would be 8. But it induces this transition probability matrix where I have 1 minus e to the minus mn chance of properly mapping or getting a y that match is my x. Now, where does that come from? So look at this output right here. So this root 8 alpha. So this is like root m, where m is 8. The probability that I don't properly detect the right one, assuming this is all done correctly, is that I get 0 detection event from this. And so what's the probability that I get 0 detection? It's e to the minus mn, right? Remember our Poisson distribution where the n is now this mn, right? Because we picked up this factor of m. So I have 1 minus e to the minus mn chance of properly getting it, e to the minus mn chance of getting an erasure. So if I get no detection events, I have no idea which one I was sent, and then 0 probability elsewhere, right? That's my transition probability matrix. Now I can do the calculation for that, and it actually turns out to be relatively simple. The marginal entropy ends up just being a lot of copies of each of the individual terms for no click versus click. And then the conditional ends up just being the binary entropy, because if you imagine each of the rows of that transition probability matrix, they all look the same just with a permutation. Long story short, this is the capacity you end up with. So I'm not calling this C8 or CM because this is not necessarily the best you could do with a joint measurement of size 8, but it is a measurement that you can do with size M. So the capacity is 1 minus e to the minus mn log 2 of m, and then you can normalize it over the number of channel uses m, right? So how does this look? Let's compare it. So again, we're looking at this photon information efficiency, which tells us how well are we doing our information extraction from each photon in this extremely low mean photon regime. This red dashed line here, this is the symbol by symbol capacity that we've been talking about with the Dolinar. The blue dashed line here is the homodyne one. So that would be the other option that you might go to if you had a BPSK modulation. And so we can see this photon information efficiency. There's already a gap between Dolinar and this homodyne. Then you see this ensemble of colored lines here. It's like a rainbow looking at you. These are all green machines of various sizes. So the smallest one, M equals 2, it's effectively just a beam splitter, and you can barely see it, but it's this solid line down here. As we increase in size, so 4 modes, which is the 2-bit receiver, green, 8 modes, 3-bit receiver, and that one you can already see here is just barely exceeding the symbol by symbol capacity for some regime. It does eventually drop back below, but if you're in the really low mean photon regime, it exceeds it in theory. And then by the time you get to the fourth 4-bit or 16 mode and up, you can greatly exceed the super additivity bound from the symbol by symbol capacity. The thing is though, so there's an envelope here under which all of these fall. And it scales like this, minus n log n, and then minus n log log of 1 over n. So I think actually, Anthony, you were correct earlier, is n log n. This is the term that differs here because we're scaling not at exactly the same rate as the Halevo. There's actually a little gap in the scaling. So as you go deeper and deeper, there is still a gap between us and the Halevo, but we are really exceeding the super additivity bound. We're going way over the symbol by symbol capacity. And so whatever mean photon number you're at when you're below, say, 10 to the minus 1, there will be, like, let's pick 10 to the minus 2 here. So if I go straight up, I can find the most information theoretic capable receiver of the green machines here, and it would be this brown one. So that's the 64 mode or 6-bit receiver. That would be the optimal green machine to deploy if you were at that mean photon number. That was all theory. We actually built this in an experiment starting in 2023 in Arizona, at the University of Arizona. And we did it using temporal modes. So unlike the previous structure of the green machine, which was more of a spatial, like path mode structure, we looked at it temporally, like you really get inside of communication systems. So the light is coming in here in pulses in time, coherent states, which in this one you can't tell which ones are alpha and minus alpha, but they're coming in. And you use switching, so like fast electro-optic switches, optical delay lines, and interference in a series of consecutive stages, and you perform the same unitary transformation that you would perform in this one. Performs the same unitary structure, but instead of being in these path modes, we're doing it in time. And we took tons of data doing this. We would attenuate our light, so we would make it really weak coming in. And if we compare really quickly, right? So here's GM1, 2, and 3, blue, yellow, green, and red. I don't know if the colors match, but we'll go back over. They kind of match. So you'll see here that in theory, the 3-bit 8-mode version was the one that might have been able to achieve super additivity. And then the 4-bit 16 mode should exceed it quite a bit. In reality, with the performance of the system, the GM3 does not exceed this black line, which is the Dolinar receiver. But the GM4, this was the first ever receiver to show super additive capacity. So this was a NASA project to try to demonstrate the functionality of the system in a like something that could be deployable. And so we were able to show super additivity with the GM4 system. This is scalable in fiber. The biggest drawback is that there's a lot of loss. So that is preventing it from being truly useful in a real system today. But we're investigating further extensions of this both in free space, improved fiber versions, and nanophotonic systems. And that transition probability matrix that I was talking about earlier, um, you can see it here. So this is actual real data collection. So
Oh,
this
this
16 by 16 here, this is the transition probability matrix or for the actual detection events. This first column is the erasure outcome. So as you might expect, it's somewhere, around mean photon number like 0.001. Most of the time, we're not getting any detection events. But when we are, then this is the normalized transition probability matrix. And so that's how we can calculate the photon information efficiency. And for each of these little circles that you see on this plot here, um, that would that comes from one collection event like this. So each circle is collecting somewhere around, I think it was like 600,000 to a million data points, depending on where we were in the plot here. And so you can see we have very, very consistent data collection here. So yeah, each circle, which probably looks like a point to you, is like hundreds of thousands of photon detection events. So we feel very confident in these results as the first demonstration of super additivity.
Yeah, I have two
If you want to
questions.
read more, you can see the publication here.
I have two questions, Jack,
Yeah.
before we move on to the poll, if you don't mind. One is mine and and then one is someone else's. When you
Yeah.
say lots of loss, you mean in the actual in the yeah,
The
processing?
receiver itself. So that's
Layers?
something we've neglected up until this point. We've always said, oh, we have a coherent state. It comes in. We assume we have no loss.
Yeah.
In reality, no, you have loss at your receiver side. So each stage, so this is, one stage, two stage, three stage, four stages. Each one here was between like 6 and 8 dB of loss, which is not actually useful for a practical system. We know we can get that down even in fiber to sub 3 to 3.5 dB per stage, potentially even better. And we know we can do better in free space. We're building a free space one. And we definitely think we can do better in integrated nanophotonics as well. So We're designing one right now and working with a foundry effectively to have that fabricated and tested as well. So we have a lot of hope that this design, actually an improved version of this design, where we've updated it quite a bit since then, will allow us to potentially deploy these systems.
Cool. And then one question, I think maybe this is a historical question or something that you might know. Someone asked, does anyone know why he called it the green machine?
Yes. Okay. That's a really good question. Here's what we're going to do. We're going to wrap up the next two slides, and then I'm going to close this slide deck, and I will open another slide deck that has the answer to that question. It's a fun question. Um, Really quickly, let's do this poll quick. Last one. Which receiver achieves C1 symbol or achieves the C1 symbol by symbol capacity when paired with BPSK? So not super additive. Which one achieves the C1? This should be a quick check on which receiver paired with BPSK achieves symbol by symbol. Dolinar is the correct answer. Those of you that said green machine, good try. That one exceeds, I guess technically achieves, exceeds. Maybe you're like partially right on that. Um, Homodyne with thresholding, not with thresholding. There is a technicality that we have not addressed here. Soft homodyning can also approach and even match C1 in some cases. But for everyone who's just listened to this and has never seen this topic before, your answer should have been Dolinar. But Kennedy's the only one that's just like absolutely wrong. But good job, everyone. We've made it to the end. The summary. Okay, so we now know a lot about how we can take classical digital information. We know what techniques we can use to modulate it, to put it into light. We understand in the specific case of the pure loss channel, which is true for vacuum free space communications. We understand what detection is capable for us and how we can leverage photon detection plus receiver side optics um, to induce channels that will give us higher efficiency with our limited amount of light. So we get more bits out of every photon. We've learned about a lot of receivers. We've covered the fundamentals of information theory, did some information detection theory. And so we now have this great context moving forward where you understand even what joint detection receivers are. There is a whole world of research out there. I just showed you something about the green machine. It is, today the state of the art. We already saw there's a gap between what we can do and the Halevo information. So we know there's more yet to be discovered. There was an earlier question about squeezing. We have some theories, and I think others do too, about how potentially squeezing could get us a little bit closer. Maybe not all the way to Halevo, but something closer. It's a really, really rich field. It has a lot of application because we are moving to an era of laser communications in space. NASA, Japanese Space Agency, Indian Space Agency, the Europeans, everyone's looking at and starting to use laser communications in space. If we're going to have lunar colonies through the Artemis program in the coming years, the plan is in action right now to use laser communications for that. And future Martian colonies are absolutely going to need to do this. So it's an open field. We don't know how to get to the best receivers right now. We just know how to beat some of the ones that have been used in the past. So with that, I'll remind everyone that there will be feedback evaluation surveys sent out. Thank you for attending. And before we go, for anyone who wants to, I will answer really quickly where the name Green Machine comes from, but let me pause my screen while I pull up another slide deck that has the answer to that. Recent. Okay, and resume screen. Okay, so hopefully you guys can see this now. So the name Green Machine, when Saikat Guha proposed it in 2011 for the optical design, he learned it from an MIT lecture, which in turn took it from a textbook that was referencing an older design that looks something like this. So this, where it really comes from, is the late 1960s. A PhD student named Richard Green was working at Caltech, along with the Jet Propulsion Laboratory, proposing the design for a serial orthogonal decoder for a Hadamard codebook. So they were also trying to do deep space communications, but they were trying to send back the first ever live videos from Mars on the Mariner 9 mission. The dilemma was that there was a lot of noise, electronic noise in the system. There was a lot of loss, and they didn't have digital computers readily available. Like there weren't FPGAs they could just go program to decode rapidly. So they needed a way that you could in have the ability to watch this video live, so you need to decode it as fast as the frames are coming in. And Richard Green, his PhD proposal was he thought, well, I could come up with a design, an analog computing machine that could implement this type of decoding for these Hadamard code books on RF signals. And so he did. He designed that. They built that. That is what they actually deployed on the Mariner 9 mission. This is a photo of Noctis Labyrinthus, which is southeast of Olympus Mons on the Martian surface. And this was one of the first photos ever sent back from Mars using that design. And so that name stuck for a little while. It was used in other Martian missions and other NASA missions for several decades. Um, it kind of disappeared. People didn't really remember the name because we switched to digital decoders, digital computing, FPGAs, and so it fell out of favor. But through a series of events of the idea from that paper or from his work, made it to some lecture notes, and eventually Saikat Guha saw it, revived the name for the optical version, which is why I sometimes call it the optical green machine or the optical green Hadamard receiver. So you might see different names that we throw around, but it is all paying homage to Richard Green and his design in the late 1960s. So hopefully that answers your question and you found it as interesting as I do.
Awesome. That's
Yeah.
cool.
So we're 10 minutes early. Anthony, anything else you want to say?
Nothing on my end. Lunchtime.
Yeah. Awesome, everyone. Well,
Okay.
I'll stick around for another 2 minutes or so if anyone has questions. But yeah, feel free to drop. And yeah, I think maybe at the beginning maybe we can put the slide up with our email addresses from the beginning, in case you want to follow up and email us anything. I'll pull that back up, share my screen. Cool. Yep. Here's this. So yeah, if you have questions or comments, you can email us. Yeah, otherwise it's been great. Thanks for being a good audience.
And I guess they'll just get an email about the course evaluation.
I believe so, yes.
Okay. Okay. Thanks, Andy. Thank you for the amazing lecture. All right. Great. I'm gonna head off. Thanks, Jack. Thanks, everyone.
Yep.
See ya.
See you, Anthony. I will answer a question right now. Radio frequency communications, the question is like, what's the future of that? That's not going away. Absolutely not. It will continue to be dominant, especially in like the near field communications. One of the big drawbacks of optics that I briefly mentioned is that you have to have like really good pointing accuracy. So if you have, large constellations like Starlink, trying to communicate with other nearby things, um, as long as you don't have needs for extremely high data rates, you'll probably just still use RF. I mean, it's well developed. Um, if you own the spectrum, you're going to use it. It's there. Now for deep space, it will continue to exist for deep space. There's a huge deep space network that's already developed on Earth with like uh, dishes on Earth for receiving deep space signals. Um, the transceivers have been developed for space, but there is going to be the backbone is going to become optics in free space over the coming decade or two, with complementary RF comms. Whereas right now it's the reverse. It's the backbone is RF and it's being complemented by optical. So that will invert. Um, maybe I think maybe I'm a little optimistic, but I think in the next decade, for deep space, we'll really start to see that change. All right, last call for questions, and we're calling it. All right, everyone. Thank you very much. Hope you have a good rest of your day and enjoy the rest of the sessions if you go to those two. So there's some good ones.